Okay, good morning, everybody who's in the morning time zone, and good afternoon or evening to everybody who's not. We're on to day two. I think we had a really good day yesterday, and we all had a really nice dinner last night, or at least I did.
Yeah.
Today we're going to start out with four talks from core team members, and Rory's going to lead us off, and then Thomas, Linda, and Chris. Rory, Linda, and Chris are in the room here, and Thomas is going to give his talk remotely. So I'll let Rory take it away. You can share your screen, Rory, and he's going to talk about Philae 3D. Find out what that is all about.
Indeed, yeah, thanks, Mike. Everybody can hear me and see it all right?
Can you all hear him? Good.
All right, yeah, so yeah, I came up with this like bit of a funny title here, which I think will become clear over time, and maybe it's clear from this first slide, right? So if you haven't heard, I'm now, thanks to Thomas' generosity, the head chef of the Philae protocol. That's part of the Cuisines Model and Comparison Project. So we're just starting to take this over. And so I thought this would be a good opportunity to sort of, just if you haven't seen it before, kind of get to know the EBM Model and Comparison Project, which is called Philae. And I wanted to think a little bit about some synergies between EBMs and GCMs. And in particular, I think this will also connect to the perturbed ensemble project that.
What is this steak doing in our logo?
That's a filet mignon.
Filet mignon.
I think that's what it is.
Do you approve of this, Thomas? I'm not so sure. Yeah.
Oh, yeah, there we go. Thank you, Thomas. So that's actually the steak emoji, which we use on the Cuisine Slack channel, but I don't think that's actually a filet mignon, but I think it is. I think it is in the filet logo there. Anyway.
It's more like New York. New York steak. That's right. Strip steak.
There you go. So let's see if I can move on here. All right. So let me just tell you a little bit about where we're going to go today. So I know that not everybody is up to date on this. So just a reminder that Philae is this model and comparison project. There's Cuisines. I thought maybe Thomas would talk about this, the Cuisines this week, but he's not. But this is a big effort from NASA to try and understand how our different climate models behave. And I'm taking over from Russell Dietrich, who some of you know, he was a former member of this group. And he did an awesome job of getting Philae started. We published our first paper last year. Some of you may have seen it at various points, but I'm just going to remind you how what we did with that today. We used two different energy balance model codes, and we've got approximately the same results. So I think that was pretty promising. And so, like I said, I'm kind of thinking about synergies between what we did with the Philae project and what we might think about doing with ROCKE-3D in the future. And just as I also said, kind of thinking at a more general sense of just how can we use energy balance models to help guide ROCKE-3D simulations. Just if you wondered, the EBM that I use, it takes about 5 minutes to run 1 million years of climate evolution. So definitely different scales here. And so
not bad.
Well, remember, mine is not accurate, you know, but it does give us a sense of maybe what climate kind of states are we out there. And what I'm going to kind of get at today is kind of thinking about boundaries, transitions between climate states, and maybe that this can help guide us as we think about, again, thinking about this perturbed parameter ensemble, which I guess I spelled wrong there. Yeah, we'll see what y'all think.
Remember, does Philae stand for something? Is it an acronym for something?
I would call it a backronym. It's the, see, I have to get it right now. It's the fidelity of ice line latitudes for EBM tenacity.
Very good.
Yeah, tenacity. Yes, thank you. I didn't come up with
it. Tenderloin.
Oh, yeah. Yeah, Russell was the one who came up with that acronym. So yeah, but it's basically about, yeah, you'll see kind of the why we came up with that name as we go through this presentation. So like I said, we published this protocol paper. So the way that the Cuisines is set up is that this first paper is designed to be sort of just an explanation of how might somebody who's getting into the field or somebody who wants to be involved with this project, what would they do in order to see how their model compares with others that are already been published, or maybe the people are developing their own EBM from scratch. There's a much lower barrier to entry for energy balance models than GCMs. And so we kind of had that in mind as we worked on this protocol. just to kind of help maybe give people some steps as to how they might develop their own energy balance model. And so we started off by identifying three what we call benchmarks, which are they started almost like brain dead, I would say, just like a really simple thing, just build an EBM and just start out by just creating like the pre-industrial, or we kind of don't care what your obliquity is, what your land mass is, things like that. Just put in 280 parts per million of CO2 and just see if you can get the Earth's surface temperature at 288 Kelvin. So that's just start there, then try and do a little better with benchmark 2, assign the obliquity to 23.5 degrees, give it something that's close to the land ocean fraction as the Earth, give it the solar constant, and then see if you can reproduce Earth's latitudinal temperature distribution, as well as the albedo of the planet. And then there was a third benchmark, which is not something that you can really compare to anything in our solar system, but just what happens at high obliquity. If you take all those parameters from benchmark 2, what do you see at higher obliquity? And as probably most of us know, when you go to high obliquity, you'll get maybe ice belts, or at least a colder equator than when you have a lower obliquity. And then the meat of the project, so to speak, is these two experiments, 1A and really 1B, but at least that's what we called them in the paper. But these are big parameter sweeps now of planetary climates. And so in both cases, we wanted to assume a G dwarf host star, and then a planet, an Earth mass planet in the habitable zone. And then we had these two different cases of a warm start, meaning the temperature sort of like what we can see on Earth today, and then a cold start where the planet was totally frozen. And with the goal of trying to map out where's the surface ice in these cases? Like when do you see polar caps? When do you go into a snowball state? When are you ice free? And we had these two codes that were part of this first paper, vPlanet, which is my baby, and then this other one is STEAM, which is a model that comes out of Trieste, and it's published a couple years ago. And so both of these codes were used to see how they handled these benchmarks, and mainly as a way to try and get the other community members. There's like a handful of other of these EBM codes that are out there, and so the idea was, well, we show you how to do it with these two codes, and then hopefully that makes it easier for other people to join in the future. So, of course, we had one goal, which was just to try and quantify how well these EBMs reproduce each other and reality. So that's the goal there. So I'm going to sweep through the benchmarks pretty quickly. This is just kind of more for completeness than anything else. But you can see this is what vPlanet came up with for benchmarks 1 and 2. And so this is on the left, you see the temperature as a function of latitude for some different assumptions and for different land types. So of course there's albedos you assign to the land and the ocean. And these are not necessarily tied to anything in reality, because clouds are sort of baked into the albedos here as well. So we can't model clouds in EBMs. And so the albedos really are meant to reflect the composition of the land and the clouds. Sorry for the pun. And then on the right, you'll see the top of atmosphere albedo. You're probably all familiar with that acronym, where you see some discontinuities due to where there's ice, things like that. And so probably you all seen something like this and have done it with ROCKE-3D, but this was what vPlanet came up with out of the box. And then with the STEAM, here's kind of everything condensed into one figure for all three benchmarks. There's these tuned and untuned cases. So that's where, if you just sort of try it with what you think should work, that's untuned. And then the tuned cases, which are the solid lines, that's when we actually tried to make things match the Earth. And so you can see here, for example, that STEAM does a great job of reproducing the inversion that you would think you'd get at higher obliquity, for example. So on the left, you see that the equator is indeed colder than the poles at high obliquity, and that's also reflected in the albedo on the right. So these are just sort of, like I said, these are meant to be little tests. I presume we've done this with ROCKE-3D many times, but EBMs can do it too. But I want to really get into these experiments, because I think this is where it really can start to tie into what we might think about doing as a team with ROCKE-3D. So these are the results for the warm start, experiment 1 with the warm start. So on the left is the vPlanet result. You've probably seen this figure before, especially if you come to like Journal Club, because this is a paper that was published a couple years ago by a former student in my group, Caitlin Wilhelm. Chris Colose covered it in a Journal Club even. And this figure is reproduced in the Dietrich et al. Paper. And so you can see that there are these different surface types or surfaces, I guess you could say, on the left and on the right. So the purple is ice caps, dark blue is ice free, light blue is ice belts, and then the white is a snowball state. And so I was really excited when the esteemed group gave us their figure on that you see on the right. It looks a little bit similar. You might notice right away that the resolution is different. There's quite a difference there, but and of course the axes, the limits on the axes on the y-axis on the right are quite a bit different. But you might be able to convince yourself that they're similar. You certainly see in the snowball state on the right, there's a little bit of an increase, and then it drops down and then increases again, and we see that on V Planet. But obviously, I'd love to see Esteem be able to do this with a higher resolution and see how close we really get to it. But nonetheless, you can see some broad agreement here, suggesting that this sort of shape of parameter space is maybe real, or at least it's what EBMs consistently will predict.
Sorry, Rory, when you say higher resolution, you just mean stepping through obliquity in smaller steps and installation in smaller steps? Is that what you mean by?
Yeah,
resolution?
exactly.
Okay.
So, right, so like I said, so on the left, there's basically a
10 to
hundred.
the 4, I didn't see that, okay.
Yeah, yeah,
Y-axis.
yeah. I added that after, as I was stepping through the slide, so it wasn't there at the beginning. But yeah, basically just more simulations in this Steam line. And then here is the results for the cold start, and here things do deviate a little bit. I mean, there are some similarities, but I'm not sure again here how much the resolution matters. But certainly if you look at, if you start with V Planet on the left, you see there's a little strip of ice belts, and they're sort of at like what 1.2 times Earth's current installation, whereas for Esteem they were getting ice belts at much lower installations. So not really sure what that means, but maybe you can, there are some similarities in the shapes of these different features. And so again, kind of gives us some hope that, there is some similarities here between the models, and that this kind of distribution of climate states is real. So that leads us to Philae-3D. So as I say here, I don't think that all parameter space is created equal. There are definitely spaces or large areas of parameter space where maybe sampling a large number of simulations with ROCKE-3D won't be very helpful, like in that giant region of dark blue. Obviously there will be different surface temperatures and things like that, but they're these ice-free regions. And it makes me think about, well, maybe some targeted ROCKE-3D runs might identify these similar trends, and we wouldn't necessarily need to run hundreds of ROCKE-3D simulations or tens of thousands of them, but maybe if we could just target them to try and identify these transitions, that might help us to understand if this is real, first of all, and then also identify important transitions, especially thinking about like the perturbed parameter ensemble. Just can we identify some of these transitions?
And do you see it as a feedback too? If they don't give you what you expect, then you could tune the EBM differently?
Yeah,
is that what you're thinking?
I definitely think that. I wasn't going to talk about that here, but yeah, I think that would be great in the sense that, there are in the EBM, there are these like diffusion parameters that basically are meant to characterize how energy moves between the latitudes. And what we do with EBMs typically is we just simulate the modern Earth, get the modern Earth right with its diffusion constants, and then just go crazy, and I mean, what really would be valuable would be to understand like how much do those change as, the surface temperature changes or the obliquity changes. And so, yeah, you can easily imagine a way to map sort of what you would reproduce, what you'd get from ROCKE-3D into sort of a matrix of values that we could use for EBM.
Great idea.
Yeah.
Do you have any way to benchmark to like Mars or something like that?
That's a good question. I mean, there are definitely Mars EBMs out there. I haven't tried that with V Planet really. Although maybe you could argue I have, but yeah. But so but we haven't done that yet. But there are definitely EBMs out there that have been applied to Mars. I'm not familiar with that literature, but it's a good idea too to think about that. So anyway, yeah. So when I look at this, I sort of saw 13 locations of simulations that I'd love to see somebody in this room do. And similarly, about the same number for the cold start. And obviously not sampled uniformly in parameter space, just really targeted at some of these transitions.
Okay, but Rory, you're showing this for your stuff, but what ESTM is very different. Don't you want to sample some of their space?
Yeah, we do. This was just for reference case.
Okay.
I mean, just saying, I didn't like these X's were drawn by hand. You know, I haven't like figured out exactly where I think they should go.
I'm not interrupting you. I keep my question for later, but it's exactly on that point.
Okay,
Because it might be more engaging. I think
Yeah.
you should not sample like that.
okay, now we should not sample like
Yeah,
this.
because you don't know that the transitions will be the same in ROCKE-3D. You might miss the point completely. You need the higher Latin hypercube approach.
Yeah, well, like I said, I think realistically, we won't nail these transitions, so I agree.
Exactly.
Yeah.
There you are.
Yeah, right, because it's definitely a different.
So you need to explore the parameter space blindly
Hmm.
and then see what these diffusion parameters or whatever else you need from the ROCKE-3D are for the different components, and then try to interpolate if they are interpolatable.
Yeah,
Use
so,
those.
yeah, I was thinking, yeah, probably, you know, there, maybe at least with this as a starting point, it might give us a sense of where we could run others that are, maybe would identify, we could at least, you know, like, for example, like in the top left, we can see, you know, I want to identify the transition between polar caps and ice-free. Yeah, maybe I start with those two where like, maybe or like an average between what V-Planet and Esteem come up with. And then, you know, maybe they're both polar caps or both ice-free, and then we know, okay, well, probably need to go in this other direction to find the transition. And so it might at least give us that information as to kind of help us be more efficient. But
One probably could draw the curves other than it crosses, so that it follows like some path just to cross.
Yeah, you can degrade the parameter space into the two-dimensional thing and a unidimensional even, and then just sample that direction and
Yeah.
see where the transition happens
Yeah.
in that direction. Yeah, you can certainly do that. I mean, the approach is very similar to what we're thinking of doing with Sunny in this project that I mentioned yesterday, and I will be presenting tomorrow.
okay,
So I think that we will be having the same issues. So might even get convinced to volunteer for it. But let's see how that goes.
all right, fair enough.
Do you know how long you would need to run these simulations for?
For ROCKE-3D or for?
Yeah. Going forward,
I just kind of ballparked it at a few million CPU hours based on ideas that Mike and I have talked about in terms of like modeling physical oceanography stuff. So I mean, 26, but probably more like 50 simulations with full dynamic oceans.
Not that much.
Not that much?
It's not,
not that.
we can run them in parallel. It's good.
Okay,
Yeah.
well, good. So never mind, then. Much less than several million CPU hours.
Thomas put a question and he said, that would be another application for the Kriging interpolation.
Yeah,
technique that Jacob was
that's
using.
what Jacob was using.
Yeah, and it's also similar to what Kevin talked about yesterday, that Kriging and the whole optimization through Gaussian processes are similar ideas. But yeah, but I think the reason why I think that's kind of not as good an idea though, is because those methods sort of assume a continuous underlying distribution. And here we're sort of looking at some discrete changes, some discontinuities, and this in terms of fraction of surface covered with ice. So that's where I think this is complementary to what Kevin talked about, and I think it's to Nancy's point yesterday too about, we know that there are these space changes, so to speak, in climates, and so how do we model them? And so that's where I think EBMs can maybe help out in terms of guiding us towards where we can identify these sorts of discontinuities in parameter space. I did want to just point out that this figure, just is, again, sticking with V-Planet stuff, is a little bit misleading because we kind of zeroed in on the region where there are these different kinds of surfaces. We did simulate up to 1.4 Earth's installation, and that's where the surface temperature hit 70 degrees Celsius, and that's where we should trigger a moist greenhouse, so those planets are probably uninhabitable. So there's actually quite a bit more of this dark blue region here than would be we might have expected. So I just wanted to point that out, make sure you know that there's a lot more ice-free space up there. And so it kind of makes me also think about, just would something like Philae-3D be worth it? Just because we're kind of zeroing in on just a small region of this habitable parameter space. Whereas there's a whole lot of space that maybe we're not going to simulate. So I thought I would just take a moment and pontificate a bit. This is for you, Mike, because you said I never pontificate. So I thought I'd prove you wrong. But hopefully I'm not going to say anything too controversial. There might be reasons just to think that that this parameter space is really more typical of any kind of planet in the habitable zone. And I was thinking too about what Tony Del Genio said during his farewell address 5 years ago or so. He said something along these lines. Can't remember it exactly, but he said in his experience that all habitable planets were going to have water in these three phases of liquid, solid, and in cloud. And so so that was what he seemed to think after his illustrious career. So I kind of have that in the back of my mind. And especially in light of the fact that if you go up to 1.4 times Earth installation, then you see something like 80% of these simulations are ice-free, which seems to go against his intuition and wisdom. But at the same time, maybe it makes me think that there's a slightly different way to look at this. I could, in principle, change the y-axis to be carbon dioxide and keep the distance the same. And just for illustrative purposes, if you did something that might look something like this, you all can tell me how off I am with my parts per million of CO2, but I think the Earth would be at 280, and at less than that, you would be in a snowball state, and more than that, you'd be, in a nice free state. And of course, the Earth has moved back and forth across these boundaries over time. And that's probably because of the carbon cycle. And it's this negative feedback, as I think all of us know, that constantly kind of seems to draw the Earth towards this boundary between snowball and with some ice coverage. And so it makes me kind of think about just, I don't know if I've seen this experiment done of just like varying it over obliquity and just looking at how the carbon cycle behaves. And maybe we really are, most habitable planets really do zero in on this part of the diagram, just like along this transitional zone. And so using ROCKE-3D maybe would be valuable because, it really would, even if you're just looking at different seven major axes, that can of course be compensated for by greenhouse gases and maybe this sort of parameter space, this sort of description of parameter space is persistent across different habitable zones. So I think that actually, if we tried this, even with only using a certain amount of CO2 on one type of star, it might still be indicative of a lot of the types of planets that are out there. So, all right, Mike's nodding at my pontification, so I'm happy for that. I just wanted, so that's the bulk of my presentation, but I wanted to just mention a couple other possibilities. Thinking about eccentricity and stellar type. So this is another figure from the Wilhelm et al. Paper where we looked at the locations of polar caps and ice belts as a function of stellar type and eccentricity. So the different line styles represent different eccentricities up to 0.3. You can see that those shapes are all pretty similar, at least for the K and the G dwarfs especially. But for F dwarfs, you can't get any kinds of ice sheets for eccentricities above 0.1. And that's probably because of this wavelength dependence of ice. It's very reflective at shorter wavelengths. You just get, it's harder to get ice sheets at higher eccentricity. So again, maybe the EBMs could help guide sort of thinking about this other orthogonal axis, thinking about eccentricity and the spectrum of the star. And then this is a plot from the paper from Hector Delgado Diaz. If you were at Journal Club a month ago or so, you saw a plot like this. This is now looking at some other axes. This is specifically looking at the planet Gliese 514b, which is 8 parsecs away and a potential direct imaging target. Just to guide you a bit here, so this is now carbon dioxide pressure on the y-axis and land fraction on the x-axis, but all uniform land fraction. So every single latitude has the same amount of land and ocean. In this case, we used an OLR model that accounted for the amount of carbon dioxide, which is a little different from what we've done before. But that model breaks down when the temperature drops below something like -30°C, which basically, as soon as you hit about -2 degrees or -5 degrees for the global temperature, you collapse into a snowball and the temperature plummets, and then the radiation model fails. So that's what's going on in the white region there. And then the colors represent different temperatures, global temperatures. And you can see again, when we vary obliquity, there are some different features to this parameter space. So again, I don't expect that we've nailed the actual positions of these parameters, but probably this trend is, I think, accurate. And so, that you can see that slope as you go from 0 obliquity to 90 degrees obliquity is increasing from where the model's failing. So that's where it drops into a snowball. There's also the peculiar features at very high land mass, where you can see it's sort of flat, the white region is flat, and then it gets perked up, and then there's like a peak, so I don't know how real those things are, but again, this is something where like down the road, we might think about trying something like this.
Your y-axis cannot be correct units, right? It's not 10 bars of CO2.
It is 10 bars, yeah.
And you get 40 degrees Celsius?
Yep, this is a very cold planet. It's at the outer edge of the habitable zone.
Okay.
You didn't tell the installation.
I did not.
You didn't
That's
say
correct.
that, yeah, okay.
I didn't say that. Yep. So sorry, that's 4 points. So this is almost at the outer edge of the habitable zone. And this is a planet that has an eccentricity of 0.45 nominally as well. So it's a very highly eccentric planet, which also increases the global temperature. So sorry, thank you. My bad for not putting that on there. And then finally, I just thought I'd show this for fun because I just did this last week. I injected into the planet this ability to change the land distribution a little bit more. I don't know if I'd seen a figure like this before, so I thought I'd ask all of you. But basically what I did is I changed the way that there could be land in this functional latitude. And so these different qualitative terms on the x-axis are different distributions of land. So modern geography, of course, that's what we have today. Uniform is, of course, where every latitudinal bin has the same amount of land and water. And I should have mentioned that all of these cases assume 29.2% land coverage, which is Earth's modern land coverage. And then there's this random where basically the mean was still 29.2 degrees, but then I let it vary by 20% from one latitude to the other. And then polar and equatorial, where I just forced the land to be either all at the poles or all at the equators. Not equators, one equator. And so, but I thought there was this kind of interesting trend that I don't understand. Like I said, I just made this figure yesterday, or not yesterday, last week. But I thought it was kind of interesting and something else that, this was trivial to do with an EBM, but maybe these sorts of simulations take a long time with ROCKE-3D. So anyway, that wraps up what I wanted to talk about today. So here's my summary. So I don't know how much time I have left, but okay, good. But there's already been some discussion, which is kind of good. That's what I was hoping for, was just sort of to get us all thinking about just, what can, EBMs do for you? I'm here in the group and we've got V Planet, and I'm now the chef for Filet, like I said. So if any of you have things that you want EBM people to do, I can use my bully pulpit to try and get them to do it. I obviously we're all volunteers, so no guarantees, but certainly I'd love to be a conduit between the GCM community and the EBM community to think about how we can have some synergistic activities here between how we're modeling the climates and hopefully get to the promised land of understanding habitable planets faster by working together. So that's it. Thanks, everybody.
Thank you, Rory. More questions for Rory in addition to?
Just one thing, as I said, that it's, I see clearly some synergies between the project that we just got funded. And we're going to do, we look into atmospheric composition, chemistry, aerosols and stuff, but we can deviate a little bit if needed. So we're doing essentially similar things with ROCKE-3D and Atmos. We want to see if we can, how close we can get the two models when simulating different things like obliquity, eccentricity, pressure, and one more thing, whatever it is, and rotation rate.
Yeah.
So we can, it's like you described our project with different models and different set of parameters, but it's essentially the same thing. So I think we should discuss.
Yeah, great.
I mean, if it's simulations you want, it should be straightforward.
Yeah, I mean, more than anything, I just wanted to see sort of, can we come up with this idea of like exploring this parameter space that we did with EBMs? Like, what is the smart way to do that?
I mean, we can take two extreme cases, start with two simulations and see what we get.
Yeah. I mean, and there's probably already some simulations sitting on a drive somewhere that are basically similar to what EBM has already done. So we'll probably start with that.
We should look at what we have. We have a whole spreadsheet full of simulations.
exactly.
I'm sure they're in there.
Yeah, and we have all these new ones that Ector has done as well. Although they've been mainly targeted at this one star, so I'd be surprised if, although maybe Andrea or
She did a few simulations.
has something that's already in that parameter.
We have a big spreadsheet.
Yeah, no, I've seen it.
Yeah, I mean, I've certainly done a bunch of obliquity runs, and we do get like ice belts,
Yeah,
and ice
right.
caps, and like we at least know the model and have those different states. But have to do the exact parameters. You
Right.
want.
Yeah. So that's maybe we should talk about that. Just make sure that we've got that one-to-one match.
Good idea. Okay, thanks, Rory. Let's move on to Thomas. He's going to tell us about the, I think, globes and PSG and generating spectra.
That's correct, yeah.
And Vincent's going to also participate in this talk, correct?
Yeah. All right, can you see my full screen?
Yeah.
Awesome, thank you. All right, so hi everyone. Thank you for having me today to do this presentation on gloves. That's very timely because I submitted the general would say general protocol paper, but the model description paper of Globeless a few weeks ago, and Vincent Kaufman here on the call as well got his GLOBES paper applied to hyper-realistic simulation of Earth, just published a few days ago. So Vincent is going to talk the last part of this presentation. And so if we start with few generalities on PSG before digging into GLOBES itself. So as many of you, probably most of you know that the NASA tool is one of the most used tool in the agency, and the website itself is very popular, and then we average like 300K hits a month. And it's easy to operate. You can either use the GUI on the web, or you can have it installed with Docker on your laptop. You can run it through the API. You have many different ways to run that, and we try to make it easiest as possible. And if you have any issues regarding the installation of Docker or the packages needed for that, please let us know. And we put together also an extensive documentation. So we have a PSG handbook that is being updated constantly. And we have some explanations of short tutorial that we have on the website. We have a GitHub. And we got a SIG proposal funded to do some live tutorials, hopefully soon. And we're going to try to what you guys have done for years with the very successful ROCKE-3D tutorials. And so, in short, what is PSG? PSG is really a software that synthesizes spectra of planets, exoplanets, and then go from a very wide range of wavelengths to the UV down to radio. And you can use it to simulate any observatory from ground and space, orbiter, probes, anything. PSG also includes a 3D orbital calculator for most of the body in the solar system. So it's quite also convenient if you want to do some work related to specific solar system objects. And the radiative transfer can be performed with several models. You can use line by line, correlated K, you can use cross-section. Basically, for any given molecules, we integrate as many lists that we can. And we have the multiple scattering that is very important. We use DISOR for that, but we had to do some development to be able to really use it for the large diversity of exoplanets and geometry. And so we convert it into a PSG dot that you can find there as well. We have also processes like non-LT fluorescence, something for comets, and we have a very complex surface models. I'm not going to go in detail to that, but you can really have a very large variety of surface with different granularity and different things like that. And the neat thing also about PSG is like once you have simulated your spectrum, you can directly connect it to a noise simulator. And so we have templates for many different observatories, but you can also define your own instrument. And so that's really, we are able to do it from the atmosphere to the spectra, and then the simulation of the noise and observatories. And so something I wanted to come back into it before going in detail to GLOBES is the difference of how the relative transfer is done in GCM with comparison to a fully dedicated relative transfer model for spectra. So in GCMs and EBMs, the mean is to reassess the energy balance, right? So by default, usually the model tends to be isotropic, and so to follow the photons, and we are really interested into fluxes for those models. We need to cover a large range of wavelengths, and typically operated at very low resolution. Even if I know that sometimes when your simulation has converged, you can really run then a few more steps at a very high spectral resolution. But usually, because they deal with fluxes, they operate with some simplification of scattering assumption, since the flux do not need the detailed geometry consideration. But if we want to interpret astronomical data, we have to deal with intensities, and that's really the key difference here. And so when we do that with a dedicated spectrum generator, that's what we get. And for example, if we want to look at transit geometry, you have refraction and different phenomena like that. But mostly what is really driven the spectra are opacities. And so the way we are going to discretize the atmosphere, so spherical versus plane parallel, how many layers do we need? Do we need sublayers? This is really going to strongly impact your spectra at the end. We saw that through the Malbec intercomparison, where at the beginning when we were having a dozen of different spectrum generator, and we really ended up to very different spectra. And the difference of that was how many layers were taking into account in the different codes. So that has a very, very strong impact. And the line list as well, of course, if you use, high energy versus high-tron, if you use different kind of, list like cross-section, corrected K, line by line, you're going also to have different spectra generated. So all those are very important consideration that we need to remember when we do that kind of simulations. And so when we do with PSG in globes, so this animation at the bottom, Vincent is going to talk about it later. Actually, the paper is now published, not in prep. So it requires really sophisticated and multiple scattering modeling of intensities, as I mentioned. Surface modeling as well needs to be accurate, and different scattering model have different effects. And the treatment of clouds is very important, as we know that if we do it in 1D versus 3D, we are going to have massive differences. And so the spatial resolution and all these different considerations are very important. So once we want to move to a coronographic simulation, then we need to have a complex regime of scattering between the day, the terminator, and the night. When we're really close to the terminator, the light is so tangential that it's super difficult for the multiple scattering to operate correctly. So that's where we had to make some adjustments there. And so if we have to sort of summarize what is the globes, so the module into PSG that really is there to directly integrate GCM and produce spectra, that would be the figure that we want to show. So if you look at the top left, what we see, we just explained that if you want to do some sort of a transit observation, you can have a realistic treatment of the limb and a high angle scattering down here by PSG globes. But you can also use the direct imaging modeling mode. And this time, as you can see, every pixel or every column of your GCM simulation, you have one relative transfer calculation performed for each of them. So it can be quite complex and expensive in computational time. But the great thing is then once you have that, you can then look at how your planetary spectrum look like at different phases. You see that at the bottom, different phase for the tidally locked exoplanets. And here we have at the top right what it will look like if you look at the phase from combined emission and reflected light spectra. And so yeah, we can really definitely connect what we are seeing at different phases with what we will get in terms of output spectra. And so instead of going through a lot of different screenshots, I figured that it would be easier that I show where we have our resource online and just navigate with you through that. The first one I wanted to show is that we had a GitHub repository. The link is here, when we have a couple of short Python scripts to convert your GCM NetCDF output with ROCKE-3D or different GCMs to binary format that is suitable for PSG globes. So should click on that link, hopefully it will open. I guess you're still now, you probably see GitHub, right?
Yes.
Perfect, thank you. So this is the conversion script between ROCKE-3D and globes. I cannot go to all the details right now, just it's right there. If you need some help, please let me know. But we put that together with Geronimo and Mike a few years ago in 2021. And so here what we are taking the AIJK file, the AIJL, the AIJ. You can have your own combination, the one that you want or not. It's really up to you, and O is your output format. But once we get all the variable we want, including water and clouds, then we have all that part here that is that are the keywords that PSG needs to basically simulate your spectra. It includes the exoplanets, the star properties, the semi-major axis, all those things like that. And then few atmospheric parameters when you put like a surface pressure, what kind of gases do you want to consider in your simulation? Do you want aerosols or not? What kind? Then you have a section very short on surface parameters. This one was very simplified, but as I said earlier, you can have a very complex surface. And then if you want to deal with some noise simulation, you can have your instrument parameters there. And finally, the binary part is really the last one here. It's taking all those important variables, including the wind, temperature, surface temperature, albedo, pressure, and send that to a binary format that globes can then ingest and simulate spectra with it. Again, it's very difficult for that amount of time to go into detail into that. If you have questions, please let me know. And yeah, as I said earlier, we are going to have a tutorial soon about that. Next one here, Sam. Of course, I'm going to show you the globes web interface itself and quickly how to use that. So here is where you are, right? So if you just type PSG NASA, don't type only PSG, you're going to get to the Paris Saint-Germain. They still have more hints than us, so we are not the first in line. But basically here is probably the PSG interface you're familiar with. Globes is here in the application. So you have different ones, globes. If you want to, let's say you have generated your binary file, you click on select a source and you can upload your own that you just did. So for instance, here is the one that, so we have for the precursor science work with PI by Maggie Turnbull, and this is a GCM simulation done by Chris Colose. And so I converted it to PSG globes user format. Loading in right now. It's going to take a few seconds because even if it's binary, it's quite heavy. There we go. And after, what you can do is you can change the geometry parameters. For now, we are in disk emission, so we can do some phase curve. But if you want to do in primary transit, you click there. You're going to modify your phase. You're going to be the 180. Here I put 90, so we are at quadrature. We maximize the separation. And you have very few parameters here on the atmosphere and instrument. If you want to change them, you click on those buttons and you're going to go back to the main PSG interface. Once you have done your change, you come back on globes. Important parameter I want to mention here is the binning. It's what is the level of binning of your simulation right now? If you have 200, that means that even if you have a very high spatial resolution with your GCM, we bin down everything to one single column. The idea is to just do a quick test, but you don't want to produce science result with that. So if you click here on generate 3D spectra, it's going to take a few seconds, and that's the really the idea behind the binning. You can just see if everything looks right, and then once you are satisfied, then you need to go and use binning equal 1, which is full resolution of your GCM. You can see here we have a spectra here in apparent albedo. It looks like expected. All right, then we will move on to the binning equal 1 to produce your actual results.
Thomas? I was going to say, for the atmosphere, you put that in the PSG configuration file, which pulled it from the GCM, right? Or we tell it how many parts per million, and then you assume it's isotropically mixed, correct?
Yes, correct. So if I go back to the planetary spectrum generator interface, change on composition, you see that everything that you had from the GCM has been included there. Because of course, then when you have no chemistry, interactive chemistry in the GCM, you have to fix yourself your abundance of nitrogen and CO2 and methane. So yeah, you have to define yourself.
Thank you.
You're welcome.
Tomas, you could probably zoom in a little bit so that you lose a bit more of the width of the scene.
Yeah. Okay, that's right. Yeah, I didn't see what you guys saying. So yeah, so basically that's the very, very short version of how to use this. But I said again, it will require more time to go into detail for that. And so something we wanted to also test is like, even if many of you here are people running simulation in 3D, as you should, sometimes, you can run a 1D simulation with single column for your own planet. It's not great, but if you want to make it better, what we actually found that instead of having one relative transfer calculation for your whole planetary disk, what you can do is to sample your planetary disk in different concentric like that, like donuts, that have the same incidence angle or the same emission angle for your light. That will just basically define for you some distinct region where the relative transfer will be equivalent. But when you do that, you really capture better the different geometry and all the light really, can scatter and go through different paths. In the middle here, you have a complex one when you put a subsampling of 10 and that your incidence angle here is from the top left and your emission is just at the center. You can really see that at the end, you have sort of 74 distinct regions where the relative transfer will be performed. Here is you see the Earth, you see the American continent, but it's in 1D, you will see no heterogeneity at all. It will be fully homogeneous. But nevertheless, it shows us that it's quite powerful to do that way to at least sort of mimic a 3D relative transfer.
So maybe you should mention that if you subsample too much, you might time out if you're using the Goddard.
Right. That's why it's always better to install everything on Docker on your laptop, then you can have in limited time. But if you use the PSG server, you can time out, yeah.
Thank you.
Yeah, you're welcome, thank you. And so those two aspects here, this figure is quite complex. So I'm going to go quickly on it and let some time for Vincent, but we wanted to test the binning on the left columns and the subsampling on the right. And so if you look only on the upper part of the plot, you have the I over F, the apparent albedo. And we have done several simulations, one for an airless planet, one for you only have single scattering or multiple scattering. When you have the B200, it means that it was a full 3D simulation, but we remove cloud and we have a perfectly homogeneous surface. And we have bin it down to one single column through directly the globes interface. And in parallel, we have the 1D calculation called no-SS with no subsampling. And here what we see is like globes is doing a great job at averaging, binning everything to one column because we exactly reproduce the 1D case. On the right, the B1 is the full spatial resolution of the GCM. And to try to match that, we use the subsampling I just described for 1D calculation. And we see that also it really works very well and able to reproduce that. We can go into detail on why sometimes single scattering overshoots the multiple scattering. Here we are in relay scattering only, so it is very forward phase function. And so you can sometimes overshoot with one single scattering when you're in a 1D calculation. It does not happen anymore when you're on 3D mode, because in 3D, you have so many scattering everywhere and multiple scattering that you really contribute to increase your reflectance at every phase angle. And so you always go beyond the single scattering. But yeah, I'm going to go into details, just showing that the binning and subsampling works very well. And at the bottom, we tested that as well for thermal emission. It's a very boring flat line, but at least it showed that it works. And now, very, very quickly, just showing some application of transit modeling. Here are, transmission spectra you may have seen many times. This was actually done with ExoCam. And the black trace is really when you take the full resolution of your terminator. But when you start to bin down, you are binning columns that are clear sky and columns that are cloudy. And when you mix them, the two, you end up with some cloudy column with an opacity that is probably relatively high. And so the more you bin, the higher you raise your continuum level. And so you end up with, more flat spectra when you bin your data. You don't want that because you kill the detectability of your spectral line. So always run your simulation of transit spectroscopy at full resolution, otherwise clouds are going to kill you. And then a secondary eclipse is also something we have done in the Martin Turbet's paper last year for TRAPPIST-1b, C, and D. We are able to do some phase curve that you can then also combine together and having a broadband phase curve if you are interested into that. Or you can have a phase curve for a specific wavelength, let's say 15 micron, and you can look at the different orbital phases and you get your contrast like that. Same thing, we have a script there on our GitHub that will help you to do that very same figure using your own outputs. All right, and now I think I'm going to give the floor to Vincent. Are you ready to take over, Vincent?
Sure, yeah. Should we keep sharing your screen?
Okay, keep sharing? Okay, no problem.
Yeah, it might be a little quicker. Yeah, so what we wanted to... 9 minutes left? Okay. Yeah, so what we wanted to do for this work is really try and validate some of the things that we've been doing at PhD, right? So the challenge, obviously, is you have a lot of information. You want to make sure that you parse it all right. You want to make sure that the simulations work well. You want to make sure that you're not overlooking anything in the radiative transfer. So that's what a lot of the paper that we just published was about. And then I wanted to show as well what we're working on now, which are some of the infrared simulations. Yeah, thanks, Thomas. You can just keep going. So yeah, what we did here is we wanted to reproduce these simulations. So these observations, what you see here is Earth seen from Lagrange point 1, June 21st. It's the summer solstice, and we have these full disk observations. It's really beautiful data, and we could get the corresponding ground-based and atmospheric information from different databases, and then use PSG and globes to run it at a high resolution and really try and confirm all of the different information streams that we get here, right? So we really want to verify that our spatial modelation of clouds works well. There's ocean glints. It's a little tricky to see in his image, but we'll see in the simulations that you could see that well. Yeah, then the other thing we wanted to do, so we wanted to do both the spatial validations and the intensities as well. So I was talking about the intensities of fluxes that we get with radiative transfer. We could get fluxes as well. There's some tricks we need to do for that, but at least the intensities is something we can directly measure from space. So the validations there would be critical. So on the next slide, I'll go into a little bit of detail how we ingested these data types. So we take the modest data type database, where we get different surface types. Then for the atmosphere, we adopt the MERA database, which gives us essentially a 3D cube of the atmosphere, right? And we consider liquid and ice clouds in each of the cells. And what you can see in the bottom right here, this is the atmosphereless planet, where we can see the subsolar point, sort of the reflections of the sun, right? And then you can see the ground variation, essentially varying with the season. So the important thing I want to point out here is that we're really, we're doing the full radiative transfer for each of these pixels. So the ground albedo varies as a function of the location, as you can see, and as a function of time. So this is really what we wanted to validate, that this goes into our codes correctly, right? So then on the next slide, we'll see the combined simulations here. So what we did here on the right, you see the observations. On the left are our simulations. So again, each of these pixels is a full radiative transfer calculation using globes. So we upload the MERA model with the ground surface and then run this model. It takes about 15 minutes for each of the images. And then they're combined with using the cloud coverage fraction map that we get from that comes with the MERA database. And as we can see here, we see that most of the spatial variation is captured very well and reproduced nicely. There are some aspects where I think there is a slight difference between the amount of cloud cover we have in the observations versus simulations, but that's something that we're still trying to figure out whether that's part of our methods or whether that's sort of an artifact of the MERA database. And we've already seen that in sort of the next section of the talk, that there is some differences between the two databases. So now here we have the spectral radiance. So it's the intensity, essentially. This is taken from the Discover data. Discover has very well calibrated their bands essentially. So the dots you see are the discover counts from their pixels, essentially pixel counts. And you can see that for most cases we very well reproduce the fluxes that we get back from our simulations. Again, there's a couple of offsets here which are sort of the 3 lines at the top, but those all correspond to locations where we have more clouds than what we see in the observation. So that's that's something that we're still sort of digging into. This is the first part of the spectral and the spatial variations. Then what we've been working on now is really looking in the infrared. So what you get in the infrared, you see on the next slide here, we're using the Aqua satellite and the AIRS instrument on board there, where within the infrared there's a lot more spatial or more spectral information. There's really much more specifics about the atmosphere, as probably many of you are very well aware of. So what we wanted to do is we wanted to take these same Mera databases and rerun these simulations, but now in the infrared, and try and match the observations in a smaller area now to our simulations essentially. So what we'll see on the next slide here is that we get the fluxes. We integrate the fluxes of this instrument between about 4 and 15 micron. Same time, and now what we see is we get the flux as a function of location. We're looking at an area above mostly the US. I picked that location because I figured the Mera database would probably be best, have best coverage there. Essentially, a lot of weather stations there. And what you can see here is that essentially the flux that you get back, as you know, it makes a lot of sense. The flux correlates very well with the cloud coverage that you see in these images. So on the next slide, you see there's the cloud coverage fraction, which is a product from the AIRS database, and on the left now you see the flux. So there's basically a very tight correlation between the two of these, which is interesting. So this is one of the main products that we use to sort of combine the clear and cloudy simulations to get to the fluxes. So if you go to the next slide, here you'll see an example of one of the pixels where the match is relatively good. You see what we have to do for these calculations is we do one cloudy simulation, taking the cloud abundance from Mera, and we do one clear sky simulation. So let me see if I can. Well, anyway, the top spectrum is. Sorry, 2 minutes. Okay. The top spectrum is the clear sky. The bottom light spectrum is the cloudy spectrum. And then when we combine this with the cloud fraction, you can see that there's a strong match between the emitted flux measured by AIRS and then our PSG flux. Then on the next slide, we see I combined a couple of these maps. So again, on top left, we have the integrated flux, the cloud fraction in the middle. And on the right, we have to pin it down to about a factor 5 so that the database overlap well. Then the bottom left is the flux map binned down from the observations. In the middle is our flux map from PSG, and then the ratio between the two of them are seen in the right bottom panel. And you can see that for most cases, there's a slight difference in the flux, but it's in the order of like a couple of tenths of percent. A lot of those differences come down to differences between the two databases. AIRS retrieves the water abundance profiles. Mera is a retroactive model, right? So we can expect it to be a slight lag between the two. And then on the next slide, we have the average over this entire area. And as you can see that there's spatial variations, but in this case, the average works out pretty well, where now we see the PSG spectrum of the full range essentially in purple, and in yellow, we see the AIRS database, which has been down to resolving power of 100, which matches our simulations. And then the bottom, we see the difference between the two spectra. And you can see that there's at the water band at 1300 wave number, essentially there's some differences. And then the edge around 700 wave number, there's some wiggles as well that don't quite agree just yet. So if we then, we'll leave it with conclusions here. So the GLOBES model has been used to predict and interpret. I say James Webb there, but it's applicable to any kind of GCM work. We've reproduced images of the Earth, including 3D cloud, various variations in ground cover and atmospheric abundances. And we verified the spectral intensities both in the visible and in the infrared. The paper is now available online. You can use the QR code there. You can get to the model, and there all of the code that we wrote for this paper is available online as well. So yeah, with that, I see there's a question. I don't know if we want to.
Very quickly, because you guys are out of time. Thank you.
Thank you.
Thank you.
You can do in the chat because we're out of time. So
Okay, two
okay.
questions.
no, there's not time for two questions.
not
Time's
time.
up. So you can use the chat.
Okay, all right.
Let's
right.
move on to the next talk. Sorry.
That's all
30
good.
minutes.
Thank you, guys.
No problem. Thank you. Okay, Linda, take it away.
So this is more of a talk about thoughts and work in progress. So a couple of years ago, I was asked to give a talk to some folks at one of the other NASA RCNs that were looking at the scale of conditions that affected the origin and evolutions of early life. And I was specifically asked to think about continentality and rotation rate. And some of this is going to be feeding into a talk that I've been invited to give to Gordon Research Conference this coming March about life under the ice in Earth history. But at the moment, I don't have access to Discover, so some of my files are not reachable at the moment. So I will share with you some of my thoughts and the things that I have right now, and I'm happy to take comments on that. So, so really for this, I want to focus on thinking about the conditions for early life on Earth, right? So, as Victor was mentioning yesterday, there's some controversy about when life first appeared. The first undisputed fossils are about 3.5 billion years. We have structures that look like microbial mats that date to about 3.8 billion years. And then there are molecular clock type studies that suggest that our last common universal common ancestor originated somewhere between 4.0 and 4.3 billion years ago. So that's quite a spread. So we're getting into that time frame also, thinking about when did substantial oceans develop on the surface of the Earth. There's also a lack of agreement on that front. You know, whether or not oceans were abundant very early on, partly as a result of steam condensing out of an initial atmosphere. Others still talk about late water delivery in the early Archean. And so we have this time frame filled with uncertainties about how much water there was, especially with respect to whatever continental crust there was. Not really continents necessarily per se, because that's a whole other question. But trying to think about, you know, where the habitats may have been in a marine setting for early life on Earth. Because one thing that folks do seem to agree on is that we needed to have a watery environment for life to get itself established and to thrive. So Richard Carlson has an interesting discussion on Hadean geodynamics and what he thinks of them in a YouTube video that was recorded as part of this initial conference. One of the first things he says is, here's what we know about Hadean geodynamics, and it's a blank slide. But one of the things that he pointed out was that if the moon forming impact was as late as 4.4 billion, then that would be a reset for conditions on Earth. So let's think about that potential as a starting point for the time frame that we want to consider. So we come to this discussion also of the evolution of continental crust over time. And as folks were able to infer from the talk that we had last week about the evolution of Venus continental crust as applied to Earth, there are a broad array of ideas based on the various criteria that you're using in terms of mineral composition of rocks and whether or not you think it was freeboard, i.e. land that sat above an ocean surface as opposed to just continental crust that was flooded. And this particular chart gives you a good idea of the spectrum of ideas. So I labeled the top and bottom axes because I thought it was a little confusing. So the top is our age in time, so GYA in geological speak, with the oldest being on the left-hand side, and the axis on the bottom is counting forward from the time of Earth's formation. So we are just about at 5 billion years. And you can see that we have everything from very little continental crust for a considerable part of Earth's history to developing a lot of continental crust and perhaps even having more than we have today, going back a couple of billion years ago. So what do we do with this? Especially since, again, our times of 3.5 to roughly 4.2 for early life on Earth really span the possibilities of this continental distribution. So another thing to consider for a planet this young, of course, is that the rotation rate is going to be much faster than it is right now. And there have been plenty of experiments done looking at atmospheric dynamics under these circumstances. Jupiter is an obvious modern example of a fast rotating planet, but similar experiments have been done for terrestrial type worlds with shallow atmospheres. And really, the shorter the length of day, the more restricted the Hadley cell, which is the main cell for redistributing heat from the equatorial regions toward the poles. You develop more atmospheric cells between the equator and the poles. And heat redistribution in the atmosphere becomes much less efficient because each of the individual cells is not as strong as the 3 that we currently have, for example. So I wanted to take a look at what would happen in the ocean, basically. So for this, I went back to some idealized continent configurations that Jeff created for us once upon a time. And for today, I'm going to show you 4 of these, plus modern Earth. So 2 of them are 25% land cover masks with different distributions. So one is a meridional, that's the A on the top there. There is also a belt continent, that's the JR on the lower left. And then I'm looking at 2 versions of 12.5% land cover split into 4 and 2 continents each. And what I was interested in exploring with this was, what is this going to do to the average temperature, the sea surface temperatures, and to the ocean circulation? So I start with just looking at what this looks like with a regular 24-hour day, right? And one of the things that we've seen for a while is that, where you have land makes a difference, but not a huge amount of difference here in the maximum temperatures that we achieve in the surface ocean temperatures. And the mean temperature varies somewhat, but it's still not unreasonable. It turns out that to have more land, which is our modern Earth 30% there, seems to crank up the temperature on the sea surface for a bit compared to the others. Now, if I switch now to looking at a 12-hour day, which could be somewhere around 4 billion years ago, we start to see some noticeable differences. First of all, our belt continent is by far the coldest, and that's simply because most of the heat that is coming in from the sun is impacting an area that is covered by land, and so there's not ocean there to absorb the heat. And with the faster rotation rate and a smaller Hadley cell, there's just not a lot of heating going on in the surface ocean, and it's very tightly adhered to the continent and not being redistributed to the poles. Right, so here we have a fairly cool max temperature and an average temperature that's just below freezing. Just above freezing.
Sorry to interrupt. This
Sure.
is Earth obliquity.
Yes, this is Earth obliquity. Yeah, the only things changed here are the rotation rate and the position of the continents.
What's the ocean then?
For these, this is a 1,000-meter ocean. So, between the 2 and 4 continent, distributions, there's almost no difference. However, they are just a little bit warmer than the 25% meridional, and rather cooler than the modern Earth configuration, which puzzled me a little bit at first. The modern Earth configuration is broadly similar to the meridional distribution on the upper right. But I think what's happening with the modern Earth type topography is that there's enough nooks and crannies driving gyre formation and recirculation of heat in lower latitudes that it can build up more heat capacity and keep the warmth there. Whereas with the straight meridional idealized continents, that's not happening quite so much. If I take a look at some of the surface ocean currents, so here's a 24-hour day again. And here, the belt continent configuration has by far the fastest velocities, and that's really because there's nothing in the way of that ocean clipping along west to east. The gyres are very tight. And it's mostly just a linear, yeah, it's hard to see with the arrows.
And these are fine resolution, right? Looks like.
No, it's 4x5.
It is, okay.
Yeah. One of the hard things with plotting the vectors is if you set the reference length large enough to see the tiniest arrows, then the biggest ones become a complete mess.
The 25 belt are gonna be huge.
Yeah, so it's a little bit tough there. So the belt continent is zipping along and it is not redistributing. You can see that there's no capacity to redistribute the heat away from the equatorial region toward the poles at all. There is a bit more happening with the meridional and the modern Earth. The 2 continent ones were sort of interesting because it's a bit like the predominant currents are deflected a little bit whenever they run into the edge of a continent, but not by much. They too also tend to run fairly linearly across the surface of the Earth. And so those max velocities also tend to be somewhat higher, but not nearly as high as the belt continent.
Are these annual averages?
These are annual, yeah.
Did you just talk ocean heat transport like directly?
I have that coming up.
Oh,
I have that coming up for the 12-hour days.
Linda, what's the albedo of the land here? You know?
So the albedo of the land here is just about 30%. We had a bare surface with no vegetation. We tried to keep that simple. On the 12-hour day, some of what we saw earlier in terms of characteristics has persisted. But one of the things that's really noticeable now is that the surface ocean velocities for all cases have slowed down considerably. There's just not a lot of energy moving things around. And we can see that in these global ocean heat transports for a 12-hour day. So these are all scaled the same. The belt continent ocean heat transport is absolutely feeble. And again, that starts because the oceans cannot absorb heat in the place where most of the incoming energy exists. I know.
Linda. You see the bloody axes here.
I know it's tiny. Yeah. So for everything but the 25% meridional and the modern Earth, you can see that the ocean heat transports basically drop to near zero in the mid latitudes, and that's mostly because there's an ice front that's getting in the way. of further ocean heat transports. With the meridional configurations, you can still you get sea ice in the polar regions, but it is not blocking the transport of heat as far poleward. So thinking about all of this, what does this mean for where the habitat space is in early oceans, where life might get a foothold? It seems a little bit like less is more with the modern Earth configuration and with some stuff that I didn't show here because I didn't have it on the same scale. The smaller ocean volumes, perhaps not surprisingly, can capture more heat energy, but it really depends where they are. Because if you have land in the way, as we see with the belt configuration, it's just not hanging on to very much heat at all. And so with the growth of continental crust over time, however, we get smaller ocean area, which we, on the one hand, early on looks like it captures more heat, but later on might be a little bit more of a problem, because now we have land that might be taking up more of the equatorial regions, again, where ocean might normally be absorbing energy. And so this seems a bit like a delicate balance of where you might find the habitat spaces suitable for life. Now, in some of the more recent papers, again, that Victor was mentioning yesterday, the last universal common ancestor might be thermophilic, but they cannot be sure. All right, so so it may not matter if it is, and if that life is getting a toehold at vents in the deep ocean, then the surface doesn't matter very much. However, if you have life like the pond scum model of life developing in shallow tidal environments, then it might matter quite considerably where they can set up shop. So, so as I said, this is very nascent ideas, and I have more work that I want and need to do on this. But I will stop here and leave the floor open for questions and suggestions.
Thank you. Biggest question I would
Sure.
think is bathymetry.
Yeah,
If you think about ocean habitability space and you don't want to think about thermophiles, that, I mean, we don't know anything about the freeboard way back when, but that could be interesting things to look at, I guess. And you probably want to talk to some oceanographers about, I don't know, how the bathymetry, from what we know, has changed, at least. I mean, probably only know what, since we've had modern style plate tectonics, but it'd be really interesting to talk to, tectonic people who think about this early period. There's this hypothesis now, which was discussed in the talk last week, about this plutonic squishy lid business early on in Earth's history being similar to what we see on Venus today. And what kind of bathymetry would that give you if you assume a freeboard of some amount, right? And that might create different kind of topographic rises or bathymetric rises, I guess you would call them. Maybe that will play some role. So it'd be, I mean, you've done a lot of work here, but I could see where you could do a few more simulations in some of the more extreme cases and just see how will that change your habitability space. That seems all obvious to me, I think. But,
yeah, and it's also entirely possible that we have continents that are not emergent.
Right. No, I'm saying even just below the water. I mean, just like 100 meters, how would that change things, right?
Yeah.
Or 40 meters, whatever it is.
I mean, like, isn't that like Zealandia or whatever?
Exactly.
Yeah.
Exactly. Yeah. Thinking about that.
Mhm.
Yes. Yeah.
One thing I was thinking of with all you need for gyres is a western boundary current. So I was just thinking in the Arctic, one of the things that mutes sea ice advance during the winter is just the fact that there's a lot of continents. I was wondering if you put some islands in that meridional barrier, you just put like things that block sea ice, if it would look a lot more like the modern Earth we're in.
Yeah, that's a good thought. So if I have something that looks more like a wedge that goes pole to pole, what does that end up doing?
Well, those have been done. I mean, Rose and Marshall have a paper on this where they have a wedge that goes pole to pole, and they've done all these kind of experiments. It's quite good. You must know about this.
It's a little different because I mean the whole point of their ridge is to create the western boundary. But I was thinking more of the fact I'm assuming because at the Arctic and you have nothing blocking the southward.
Right, if you just
retreat
want
of
some
sea ice.
disruption,
Yeah,
yeah.
if you want to disrupt that southward extent of sea ice, I can imagine that the climates with a more similar to Earth.
That might be like a realistic thing too, because there were hypotheses for a long time, Linda, about these microcontinent ideas. I mean, much smaller than what you've shown here. So
yeah.
imagine you have these kind of almost Hawaiian island type things popping up all around. That would be really cool. I don't know if that's what it looked like. Maybe it did. Who knows? I mean,
nobody does.
or if you look at the rises on Venus and you assume that the highlands on Venus are produced by things like that, then you could see there would just be a few places if you had a high freeboard where things just pop up in those areas. That would be really, and Matthias and I did these simulations many years ago, using modern Venus topography and then changing sea height and seeing how dissipation works, and that generates heat also in the oceans itself. So there's a lot. I think the parameter space is monster.
Much parameter space.
But we use this Otis model to do a lot of that work. So you could do a large parameter sweep with this Otis model.
Oh, okay.
And then you do subsampling of the Otis, kind of like we were talking about with EVM.
What's
Otis is an oceanography model that runs extremely fast. And it's simplified from a normal ocean, but this is what the oceanographers out at Oregon State, I think they're the ones that developed it, right?
Not very sensitive question, but I recall that this work the results were delayed because there was some issue with Planet 1.0. And then I guess that must have been resolved now.
Oh, I ended up needing to switch to Planet 2.0 to change the rotation rate.
You couldn't change the rotation rate, or I thought there was some other issue.
No, that was my main problem.
No, we changed the rotation rate in Planet 1.0 all the time. What do you mean? That sounds strange.
It would not work for me. All of my runs crashed.
Well, it crashed how? In the ocean? Because we've run tons of simulations with Planet 1.0 different rotation rates.
I don't remember the error message, but with these continents, it just was not working.
I mean, didn't you run some continents like this too?
Yeah,
That's
I
weird.
remember.
Okay.
Maybe something good happened in Planet 2 then.
Well, something good did happen in
Okay.
Planet 2 because
The
I was
ocean
able to
is
do them.
I guess all your runs were run with the land points at the South Pole. But that's so. I talked about it during my talk, but we are sorry.
Planet 2 has that same issue.
Yeah, that has the same issue, but we're working on it with Gary to remove the land points and have a full treatment of the ocean dynamics. So maybe it would be interesting. The Southern Ocean might have a totally different dynamics once you have a full treatment there. So maybe it would be interesting to redo some of these roads.
Oh, yeah. No, I definitely, I have some very specific things that I want to redo, but I had different permutations of the different runs, and so it's a little just scattered at the moment.
Kaushal had his hands up. Let's someone online. Go ahead, Kaushal.
Hi, Linda.
Hi.
Great presentation. I had a comment about the subtropical ocean circulation.
Sure.
So the meridional extent and the zonal extent of the ocean basin, the ratio between the two, actually would determine the strength of your subtropical circulation. So if you had in one of the runs you had two continents placed such that the ocean was narrower, so you would have a faster subtropical circulation there, and when the ocean is wider, the circulation would be slow. So keeping the land area constant and just changing the distribution of the continents could tell you a lot to the first order about the circulation in the ocean. So it might be fun to look at that. Just a comment if that helps.
I think so, yeah.
It's just hard because like once you start thinking about that, the degrees of freedom go so high. It's like it can be crazy because then you introduce topography and bathymetry on top of that. It's like there's just way too much space to.
We're very successful expanding perimeter space.
Yeah.
I mean, I'm not talking about topography at all, just changing the position of the continents. And I have a framework if you would like to use that to analyze that. Be happy to send over the relevant papers. Linda, if that helps.
Yeah, no, that really great point.
No, I was just making the point that once you start pulling that thread, everything you're gonna have to start doing everything.
I agree, and this is one of the, I think, very important questions. We don't understand the role of the distribution of the land as to what effect it has on the ocean circulation and the climate in general. It is, I'm very happy to realize that these simulations exist and these can answer some very important questions. So I'll be happy to take some of them off of your hands and analyze it, if that's okay.
Yeah, no, we should definitely talk more.
Yeah, absolutely.
And one more online. I think, Scott, you had a comment?
I just put it in the chat. Nothing I need to say to the group.
Okay. Go ahead, Nancy.
Did you look also at the climatology on your continent?
I have not looked at the.
That was my question.
Okay, that definitely should do that because, you know, the rotation period, how much continental interior effects versus, you know, otherwise. And also, is there nothing, nothing we can do yet to constrain where land masses will accumulate on planet? I mean, from our solar system, there's no kind of information to constrain that.
No, there's this plutonic squishy lid idea I was saying in the beginning.
Yeah.
That might tell you what the Archean was like, if that was the tectonic state of the Archean, but we don't know.
I mean, we've got Mars, we've got Venus, and
but they don't have plate tectonics like we have today.
I don't think there's any generalizable thing.
Not really.
Yeah, I mean, we can't even figure it out on Earth, like your first slide that had all the continental growth models. We can't figure it out.
I mean, the only thing I've seen remotely like that is for planets orbiting M dwarfs that are so close to the star that they have that.
Did the surface air temperature, does that track with the surface sea temperature?
It does pretty closely. Yeah.
Then I would imagine that, and I'll show some of this stuff tomorrow, that when you have land around the equator versus land at the poles, at that obliquity has to do with like the albedo at the poles. And so if you have land at the poles versus no land at the poles, it's like a big driver of that. So it changes your albedo.
Yeah, and with these, there is I didn't have maps for all of this, but there is significant snow and ice accumulation, which is also gonna change that.
Yeah.
One more, Rory.
I was also wondering, just to keep adding to parameter space, have you seen this paper from SEALs in Antarctic arguing that the amount of water on Earth's surface has increased by a factor of 5 over the last 4 billion years?
No, I didn't see that.
I was thinking about it in terms of you said 1,000-meter deep ocean, and so like a 12.5% land. I mean, maybe that you could even have a much smaller ocean. Maybe it's like 100
I could
meters.
certainly try that.
I don't know, that could really start.
Corinaga has a paper also about the freeboard through time, but I think it's a lot of speculation.
Yeah, it's speculation for sure. But there are reasons to believe that water could cycle between the mantle and the atmosphere.
It does now.
Yeah, so it could be that, as the Earth is cooled, more of that water has been spat out. So, I mean, there's intuitive reasons to believe it. So but once you get to sort of a really shallow ocean, that could really change the climate, of course. So it might be an interesting knob to turn.
It'll go on the list of simulations to do once I can get back into Discovery.
Okay, let's slide on to our next speaker, Dr. Colose here. And we'll take a break afterwards.
See this? All right.
Yep.
So I'll talk a little bit about two projects here. The first one, I've been working with Maggie Turnbull and a few people here. Arthur Adams is a grad student, Stephen Kane, Aaron Morelli. This is, so I ran 93 Earth runs that have, well, Earth atmosphere, Earth continents, but different orbital parameters, obliquity, rotation rate, eccentricity, and just the longitude of periapsis, which I won't talk too much about, but it doesn't matter that much. And we just went from 1 to 294 Earth days, obliquity to 0 to 90 degrees. So there's kind of a whole sampling parameter space. We don't go to super high eccentricity up to 0.225. And we're interested in just some things about the habitability of these Earths. I just want to kind of give a sense of like what the, how solar insolation behaves at very slow rotation when, for example, this is a 256-day rotator. And so, the sun is moving pretty slowly in the sky from east to west. And so your seasonal and diurnal cycles blend together. This is for a high obliquity planet. If you went to a low obliquity planet, again, it's just kind of moving east to west slowly throughout the year. On some time scale, you'll kind of switch from a kind of quasi-geostrophic climate that we live in now at fast rotation to a diurnally driven circulation. This is just a box and whisker diagram of the monthly zonal, the east-west range in temperature at the equator. So, at some point here, you start to see very big east-west gradients in temperature that, we don't see on modern Earth on that monthly time scale. I just want to kind of go through the maps from ordered by rotation rate. So the obliquity is labeled on the axis, and you can kind of see the, when you get warm tropics versus warm poles, but the graphs are ordered by rotation rate. And so as I move down these plots, we're going to slower rotation. And so as I continue to do this, you're going to start to see the planets get a little bit cooler and eventually, so now we're in the, kind of 100+ day rotation rates. And the other thing is all these planets kind of look the same, right? If I was to ask you what
Hold on, I'm so confused by what you're showing here. Can you please go back to the first slide?
Yeah.
Your arrow is showing slower rotation rate going down. So you're saying that
so
as you're increasing obliquity, you're also slowing the rotation rate?
No.
Then why does this arrow point down?
The maps are ordered by rotation rate. So
what do you mean the maps are ordered by that?
As you move down the map, as you go to the bottom panels, as you go to the right, and as you go to the bottom of the plot, the rotation's getting slower.
So you're saying that obliquity 50 has a faster rotation rate than obliquity 70 on the left?
There's no relationship between the obliquity and the rotation. It's randomly distributed. It's just as you move down.
I didn't say there's a relationship. I'm just saying that's the fact. So obliquity 50 on the left here has a faster rotation rate than obliquity 70 on the left here.
Correct. Yes.
Okay, thank you.
Yeah, and so this is the second panel. So these all have slower rotation rates than the first panel, but again, rotation slowing down as you move down this plot.
About how much? Like, what are we talking about?
Yeah, I should have said something. Yeah. So okay, I'm gonna show something more concrete that gives a sense of the rotation sampling in a moment. But as we get to these plots, we're getting into intermediate to slow rotation.
What's that? What does intermediate to slow mean?
I'll show you a plot in a minute. Be patient. Okay. But
Good things will.
all right, good things will come. All right. But consider Coriolis effects negligible by the time we're at this plot. But all these plots look the same. So if I was to, ask you what's a 0 obliquity planet, what's a 60 obliquity planet, it's hard to kind of see the differences. And this is just the last few on the map. All right, so here's something like, so here's rotation rate on the x-axis, and you can see the data points. So we're the sampling, from 1 to 10. This is a log axis, so from 1 to 10 days, there's a lot of data points. 10 to 100 days, we only have a few data points above 100 Earth days. But one thing we see is that the global temperature is in dots, and it's color coded by obliquity. one thing I wrote a whole paper about how high obliquity Earths are warmer than low obliquity Earths, and that's true at exactly 1x rotation. Although it doesn't seem to be true at intermediate rotations, and so that's something.
So in these simulations, they're modern day Earth,
Modern
purely
atmospheric topography, yes.
albedo, vegetation, everything is modern.
Well, albedo,
1850 pre-industrial.
yes.
Okay,
Yeah.
so it's like the P1SOM40.
This is actually P2, but it's
Same difference.
yeah, but it's the modern Earth rundown, just changing the orbit.
Okay.
Yeah, and so you see
So you have vegetation?
no, there's no vegetation. No, yeah.
Just after, and you said there was.
Sorry, no vegetation. I didn't think you mentioned vegetation in it, but the no vegetation and no ice sheets, and the reason is because we're sampling a very large orbital parameter space. We don't know how vegetation or ice sheets are going to respond.
Would you set the albedo to for the land?
And
No land ice?
there's no land ice.
What's the land albedo?
We don't know what ice sheets. They're not dynamic.
Land albedo.
The land albedo is the classic bare soil mixture that we use with I think 20% albedo before it gets wet or before snow falls on it.
Okay. Fine.
All right. So a few things that stand out. One is just this trend toward colder global mean temperatures as you go to slow rotation. And also there's really no spread between high and low obliquities. And again, there's some eccentricity information in here, although the effect's small. So I ended up not really plotting things in eccentricity space. All right.
We could add some of our climates 1 data to this, and if they have zero obliquity or eccentricity, and we go to quite slow rotation range. Just to mention, we could add more data points to if we want.
All right. All right. The questions are coming in, so I'm going to skip dynamics, I think. But I'm just showing. I'm showing.
Too much information. Get more questions.
No. Well, I'm just. I'm starting to work out some reasons for this, and I mean, this is just how Earth partitions the poleward heat transport in between the two fluids, ocean and atmosphere, and poleward of 20 degrees. Most of the heat transport on modern Earth is done through the atmosphere, not the ocean. Although the ocean plays a big role in holding back the sea ice edge, but most of the heat transport's in the atmosphere outside the deep tropics. And then I just plot the maximum heat transport in the atmosphere and ocean, the absolute value according to I say ensemble member, but again, it's ordered by rotation rate. So you're kind of seeing again a lot of the heat transport by the atmosphere at slow rotation, and then it becomes more comparable with the ocean at slow rotation. Anyway, I'm also trying. This is just a thought.
Oh, so can you just back? What do you mean by maximum? You mean the peak of the previous curve?
So the peak, the absolute value, but it's the peak of the previous curve.
Okay,
the maximum heat transport. That's what I plot here. I'm also I've been trying to do some test runs because I kind of want to isolate the effect. Well, there's kind of two things when you slow rotation down. One is you change the dynamics to the Coriolis effect, but you also make the sun just move slowly in the sky. And so most of the land points are just sitting there in darkness for most of the year. So I've been trying to do some test runs where I actually speed up the orbital period, just playing God with the model. Obviously, so this is a 36-day orbital period instead of 365 days. You can't do that with Kepler's law. Earth would be well inside the orbit of Mercury, but just we can play God with computer models. And so the sun now moves west to east when I do that. But this just shows that the sun is moving fast. It's also leaving every area fast too. But again, even when I do that, I get kind of this, this is just with a small sampling of runs on the right side. At fast rotations, I get kind of hot temperatures, and at slow rotations, I come back to these cold temperatures in the global mean. That's just kind of a thought I had to isolate the effective dynamics from just how slowly the sun moves. Precipitation, again, I play movies, and so the precipitation, kind of follows the substellar point. This is for a low obliquity planet. You get these kind of monsoons. This next plot is for a high obliquity planet, so you're going to see more north-south migration of the monsoon season. And so we wanted to tie this to a habitability metric that has some.
Are there's monthly time steps?
This is monthly time steps, yeah. And for people not familiar with ROCKE-3D, a month means something different for each planet. When you have a 256-day rotation rate, the calendar system is dividing the rotation into 12 segments of unequal length in some way. And so a month here might be, you know, a long time, but all right. So, but we're trying to combine temperature and precipitation a little bit into some kind of habitability metric. This is, people always argue with these metrics correctly, but it's kind of a start when you're just doing some temperature above zero criteria over land, and then, you know, it has to have some threshold of precipitation. And so when you do that, and we'll show the fraction of time. So again, using monthly data over, say, a 30-year slice, what time percent of that time is spent, is a grid box spent in a habitable condition, right? And so you can plot that here. And again, so your habitability fraction kind of looks like temperature, in the sense that if you were to take a land point at slow rotation and ask what fraction of the year is it above, most of this is driven by temperature, what fraction of the time is it above zero? It's very small. So most land is, you know, 20% of the time, for example, is so this is a global and time average here. So I don't want to spend too much. You can also do like some climate zone stuff. This is kind of an Earth-centric thing where, you know, people interested in like Köppen zones and things like that, like to split up a region into tropical or arid or temperate, depending on temperature thresholds, either in the annual mean or the monthly, or you know, variability, precipitation variability, right? So if it's hot and dry, or if it's hot and wet, or if it's wet throughout the entire year or only wet for a month, you know, that's more of a monsoon region versus a rainforest kind of thing. I very quickly simplified this into a couple different regions, a couple different criteria, and the top two panels are fast rotation planets. The top right is a high obliquity planet, and so you kind of get these arid regions at the poles. The bottom two panels, and I didn't show every map, but pretty much every slow rotation map looks like the bottom two. It's tundra and cold, or polar and cold. So all these slow rotation planets are tundra planets. They're kind of boring and cold and lifeless and dark. So
Hot.
yeah. So and
on the land.
yeah, on the land. Yeah, the oceans have a lot of heat capacity, so that, you know, talking a little bit about heat stress, I would, you know, I was thinking at you know, the slow rotation. Okay, it's dark most of the year, but then, you know, once in a while the substellar point is overhead and it spends a long time. You know, if you're sitting there in Africa, maybe it's, you know, it's bitter cold for 11 months, but then 1 month it gets really hot because the sun's overhead. But actually I should go to the next plot. Actually, you don't really have any heat stress though, defined by a wet bulb temperature, which is something that people use in the Earth community to quantify heat stress in mammals. Like humans, if the wet bulb temperature is above like 35 degrees, if you were to walk outside, you know, naked and spend a day outside, you could die, right? So, but there is no heat stress at any of these slow rotation rates. There is a little bit at the high obliquity runs, again, and that's just going back to this map. Sometimes at the poles you get these high wet bulb temperatures, but so we're not concerned about heat stress. We're just concerned about the dark, lifeless, slow rotation planets. All right. Moving on quickly to the next project, very different. I'm just going to reorient your brains to now low mass stars. I also did another large ensemble sampling a lot of planets around 2600 or 3000 Kelvin stars, kind of following, you know, like the Ravi-Kaparapu method of you know, as you move a planet closer to the star, you change the rotation rate, just being consistent with Kepler's laws. You change this, so you're changing the solar flux and the rotation and orbital period self-consistently as a function of distance. I used Rory's software, vPlanet, to calculate the geothermal heat flux as a function of that distance, just assuming a constant Q value for the tidal dissipation, kind of a simple calculation. But I wanted to expand what a lot of people are doing. Instead of just a synchronous zero obliquity planet, I'm giving it a little bit of eccentricity, or some obliquity. And after conversations with Rory a while ago, I've been convinced in multiplanetary systems, for example, you can achieve these perturbations, at least at some frequency, and generate tidal heating, right? If you have an obliquity induced bulge or an eccentricity induced tidal bulge, that can generate a geothermal heat flux. And so I just sampled zero obliquity planets around these 2600 Kelvin stars with a moderate eccentricity, and then I just said, you know, maybe we can have a 90 obliquity planet around 3000 Kelvin stars. I said no obliquity, that's an error. That's no eccentricity. So the geothermal heat flux is on the bottom left here for these two. I also did 3-2 spin orbit resonance planets. I'm not going to talk about that today. But because the planet is getting closer to the star with increasing stellar flux, you not only get increasing stellar flux, but you get increased tidal heating that kind of adds to the stellar flux.
What are the units on the y-axis?
Watts per square meter.
Okay, thank you.
And now one thing I wanted to, and the bottom right plot here is just the obliquity, what stellar installation looks on a synchronously rotating world at high obliquity. And so it has this sort of hourglass pattern. Actually, if you do a zonal average of this, you actually get the familiar structure that the poles get more sunlight than the equator. But for a synchronously rotating planet, you get this kind of hourglass pattern in which the sun moves north-south. There's also some east-west movement because of the equation of time. It moves the substellar point a little bit, even for a synchronously rotating planet. But this is what the annual mean insolation structure looks like. Now I also applied tidal heating. What I wanted to do is not just do a uniform application of the tidal heating, but apply it to the substellar point or the antistellar point to sort of reinforce the solar heating or to counteract it. And I did this for ridge worlds and aquaplanets. The purpose of the ridge was, and I won't show aquaplanets, but the purpose of the ridge was really to hinder some of the ocean circulation from just redistributing the geothermal heating. And so there's some movement from inside the ridge to outside the ridge, but the aquaplanet kind of smoothed things out a little bit too well so the results kind of weren't too interesting. But so these three cases, these had the same global average geothermal heat flux, but one is just applied uniformly, one is in the substellar point, and one's at the antistellar point. And I'll just show some results for a few cases. Well, this is for all the cases around the 2600 Kelvin star. So this is snow ice fraction, which there's some differences between. So ASG is the antistellar heating, SSG is the substellar heating, and uniform heatings, right? So you'll get some difference so I'm kind of just testing different regimes of how the tidal heating is manifest in the planet. And so there's some there's quite a bit of dependence comparing, like, for example, ASG with the other curves in what your global snow ice fraction looks like depending on where the tidal heating is applied. And I'll just show a few case by case examples. So this is a case, same stellar flux, same global mean tidal heating, but this is where the tidal heating is applied uniformly. I say symmetric, it's uniformly across the planet. And then the right panel is where it's applied at the substellar point. And so it reinforces the solar heating or the stellar heating. And so you get a thing of liquid water at the substellar point, but not when it's applied uniformly. And then these are the other cases. So the top row is 0.6 stellar flux. You get liquid water at the substellar point, but not the antistellar point. But on the right, you start to get liquid water in both areas. All right. And as you go to 6.65x solar, so we're increasing the stellar flux as we move down the panel.
So
Right.
there's so many plots here, Chris. Is this uniform geothermal heat?
No, it's the left is SSG, it's substellar. The right is ASG, it's antistellar.
Okay.
Okay.
Fine.
So as we move to 0.65 stellar, we again open ocean at the substellar point, but it's ice covered at the antistellar point. Now the right plot is you kind of get ocean everywhere, and as you increase the stellar flux further to 0.7x. You're starting to see some spillover of ocean water onto the night side, but the antistellar heating, the whole ocean is open, and so the point here is that even for a given stellar flux, a given geothermal flux, the location of that geothermal heating relative to the substellar heating matters for kind of whether the day and the night side are both ice covered or whether they're one side is one's ice, one's liquid.
What's the magnitude of the geothermal flux? I might have missed it.
Yeah, this just goes back to this plot. I mean, so it varies as a function of distance, but it's we're looking. These are pretty large values. I mean,
Okay.
we're looking at
20,
30. So this was the 0.6 to 0.7 is if we just go back 0.6 to 0.7, we're looking at the blue dots. So we're looking at 25 to 40 watts per square meter of geothermal heating.
Okay.
Again, it increases with stellar flux because it's getting closer to the star. But the global mean is the same in all of these plots. It's just distributed differently between the antistellar and the substellar areas. And this is just two other examples at high obliquity. So this is a high obliquity planet. They're both 0.55x stellar flux. But the one on the left, the tidal heating is applied at the substellar point, and the one on the right is applied at the antistellar point. And when you apply it at the substellar point, you get open ocean. When you apply it at the antistellar point, both are ice covered because they're both not having enough energy to melt. So again, the point is that the distribution of the tidal heating matters for kind of your snowball, where you snowball.
Shouldn't it be well defined? I mean, where the tidal heating is supposed to happen? Just
Why?
from general physics, I don't know.
No, planets are more complicated than that. There's people that have made predictions for like where the volcano should be on Io, and they're exactly wrong. So I can't remember now which way it goes, but there's models out there that people have published in like the last decade saying, oh yeah, when we do it through physics, we should get all the volcanoes at the equator and around the pole, or it's vice versa. So it's really not well understood. And I mean, it just comes down to the nonlinearity inside the planets, right? You get a weak spot for whatever reason, compositional or a stress or an impact, and then that becomes a hot spot.
So it's rheology dependent.
It's rheology dependent, and it's just,
That's why when you see these tidal heating models for TRAPPIST, they're all over the place, right? Because people use different rheologies.
yeah, for sure. And they make global averages and everything, right? So it's just, planets are hard.
They're just so heterogeneous.
Yeah, exactly.
How would you ever figure that out?
Yeah.
And that was the point of why I wanted to sample different tidal heating spatial structures to see how it reinforces or the substellar heating, or if you apply it on the night side, what you can do to the global ice cover. Anyway, I'm done.
More questions for Chris? Yes, Dr. Barnes?
Yeah, that was all great stuff for sure. I love the exploration of the parameter space, but I have like 17 questions. There's so much stuff to talk about, but I guess there's this one question and one suggestion. So my question is getting back to the whole, the global temperature drop for high obliquity and sort of that intermediate rotation.
Yeah.
I thought that was fascinating. Do you know why?
Yeah, I don't know why right now.
I mean, so
Wanna
like,
show
it's
that
like,
again?
Yeah,
the
so,
Earth is just, so the Earth's rotation is sort of just special for that. I mean, that's like everybody comes up with that same result, that
yeah,
higher
and
obliquity results in higher sort of global temperature.
yeah, and we
then
haven't
it's just
done
all
any,
because we've done it in one day.
yeah, and we haven't done any, like Linda did faster than Earth rotation. We haven't done faster than Earth, but,
Yeah.
all right, so this is a log axis. So I guess, we're looking at 9 days or something. In which, so the rotation rate, the high obliquity runs are colder than
By a lot.
than the low obliquity runs. We do see in a lot of cases where the intermediate obliquities are warmer. And then as you go to very high obliquity, presumably just because the equator is shielded more, it's
This could be related to continental layout, just like we see when you have,
yeah.
these barriers. So people haven't looked at that for those higher liquids. It could be you just have limits in ocean circulation. It just doesn't allow transport, and then that's what you get. That's probably exactly what's happening.
Yeah.
What else? That's the most obvious explanation. Right?
Yeah. So it'd be fun to do this with different continents or even an aquaplanet, but
because that was shown in that paper that we wrote with Tony, right? Where we put the substellar point over the Pacific, and that was very different from putting it over Africa, because these boundaries show up, right? And then you have no heat transport, and that plays such an important role there.
And,
I'm sure it's
and also Antarctica is a huge mountain.
Yes.
It's not just like
exactly
Africa plain or something like that, right?
Yeah.
It's really a huge mountain.
Yeah.
So it can be very surprising.
Yeah.
Scott said something too about his ancient Mars.
But it's not, it's not obvious why modern Earth, if you increase the obliquity, the temperature gets hotter. But if Earth had a eight day rotation rate, now all of a sudden increasing the obliquity cools it. Like that's not straightforward.
We do see that in the EBM runs, where like increase the obliquity and the surface temperature goes up, and that's sort of rotation rate independent, right? We just assume the rotation rate is fast.
Right.
You're changing the size of the Hadley cells. You changed.
Yeah, so that's probably
where things go through. I bet all this can be explained out of these dynamic processes.
Yeah, and I guess I was putting the thought of reminding me, I was also wondering, thinking about Hadley cells is at like, you have this phase change at like sort of 30 or 40 days or something where everything just drops and it's all about the same. And that made me think about, is that where the Hadley cells go to the pole? But I think that's lower.
The Hadley cells do go to the pole certainly by this point, but again, this is another thing. Like, why does the climate not care at all about the obliquity at these slow rotation rates? I also don't have a clear answer for that.
But I think your intuition's right, that it's probably the atmospheric dynamics are probably pretty similar.
Yes,
and it's not.
Oh yeah, it's certainly a global Hadley cell. Yeah, there's no correlates effect to that.
And then the suggestion I was thinking about was back to the tidal heating was, I thought it'd be fun, I don't know how much time you have, but to actually take the locations of like, say, the 10 hottest spots on Io and put them on your planet as well. So sort of like take the solar system and maybe that's a representation of how tidal heating really does get expressed on a surface.
Yeah, in a heat pipe, with a given rheology.
Right,
which is completely different.
But at least we have an example.
I like that idea, taking your
geyser rules.
I think you're better off using Venus. It's more like Earth. It's probably got a rheology closer to Earth, and we know we have some ideas of where the hotspots are.
We know two now, right?
Yeah.
But where Io, we know where all of them are.
Io is too close to a huge planet, right?
You can see the gravity anomalies in Venus, and you can assume maybe where the crust is thinner, there's more upwelling. Therefore you get heat. And that,
Well, these two plots on the bottom are like the maximum reinforcement of the substellar heating and like completely opposite of the of where the geothermal flux is put into the night side.
I love the end numbers there, but
that'd be fun.
So Sonny was saying, could this be an artifact of the single value plot? So the maximum temperature ranges, median temperatures differ. Not sure exactly.
And so you're saying instead of doing dots for every point, make a box and whisker.
Box and whisker of
the whole range of temperatures on your planet instead of the annual of the globe.
The one with the blue, green, and red.
Yeah, I understand. That would be interesting. This is global.
Scott says, for what it's worth, in my ancient Mars simulations, high obliquity also had colder temps relative to low obliquity. But Scott, do you mean for the ones that are land planets, or are you talking about the ocean ones? Which ones?
These were land planets.
Okay, thank you.
Yeah.
Yeah, I think Mike, we had opposite thing, this ocean runs, so I don't know, you
Well,
probably
we can't
remember
say that
better.
because it's such a tiny ocean, but yes.
Yeah, but I thought that like high obliquity planets were in general warmer or just locally warmer.
No, I think it was
or really
colder.
needed it.
I think it was colder.
Huh.
I think that it was colder in the habitable region.
So this is a really naive question, going back to your IO point, which
Last
I really,
question.
which I really like. The mass ratio between Jupiter and Io and TRAPPIST and any of those planets, would that play into like having similar tidal effects or?
Well, you have a lot more energy just because the masses are larger, so that's one of the things.
In which case?
So the star and planet has more mass than Jupiter and Io.
Right.
So generally, that's why you can get Io-like heating for much lower eccentricities on an exoplanet for like say like TRAPPIST-1b.
Right.
You know, it needs an eccentricity of like 10 to the minus 4 to get Io-like heating.
Okay.
And same whereas Io's eccentricity like point is 10 to minus 3. So you can get a lot more heating just in general because there's just more mass, so you have more energy. So I don't know if that answers your question. I feel like I went off topic a little bit there.
Well,
But,
I mean, like I said, this is very naive, but like I was thinking that is it a function of the difference in
the mass
mass
ratio.
between the two objects that are orbiting each other?
I mean, that does definitely enter into the equations.
Yeah.
You do have a mass ratio.
Because I was just trying to say, if
So,
you were to make an argument of extrapolating Io to a TRAPPIST like mTOR system,
Yeah, and I think
could you argue for?
yeah, right. So
Yeah.
that's got to be part of it because like Io to Jupiter is like 10 to the minus 6,
Okay.
and like
Yeah.
then a TRAPPIST-1b say the TRAPPIST-1 is like 10 to the minus 4.
The magnitudes would be different, but you're saying to just put hotspots in where.
Right.
Yeah.
Those are-
Okay,
Extremely tidal heat worlds.
let's take it to the break. We'll take a break now for 30 minutes and we'll be back. Putting back on. Okay, Diogo, can you please share your presentation and tell us about your fascinating research on Venus's oceans?
All right, so let me see. Let me know if you are seeing my presentation or not.
We see it. Looks very good.
All right, so may I start?
Go for it.
All right, so good morning, everyone. Good afternoon from my side, from good old Lisbon. Today I'm going to present the result of our modeling work with ROCKE-3D on the ocean circulation of the paleo-Venus. And this is the result of the coordinated effort between me and Michael and Mike, and all my PhD supervisors, Matthias Green, João Duarte, and Pedro Machado. And I'm a PhD candidate in physics and astrophysics at University of Lisbon. So let's getting started. So one idea about, or two leading ideas about the past of Venus lead to two different scenarios. One possibility, Venus billions of years ago, says that the planet could have a temperate climate, and some studies suggest that physical processes might enable habitability in the very beginning. Other studies say that water vapor didn't condensate in the first place, and we end up with the present-day Venus in the very early stage. So these are at least two possible scenarios. And today I'm going to build up on the first one. So we are considering that there were benign temperate climate at the very beginning, just after the ocean magma formation. And we say that based on the simulations by Way and Del Genio 2020, that there was a rapid cooling. And as you can see here, I don't know if you can see my cursor, but in the plot, you see the time in gigayears, and you see in the y-axis the mean surface temperature. And so according to this scenario, what we are considering is that there was a rapid cooling leading to water condensation and formation of an ocean on Venus. This ocean might have led to tidal dissipation, and it was according to a work by Green et al. In 2019, where they used a tidal model to prove that a short-lived ocean with a mean depth of 330 meters can host a solar tide with 0.5 meters amplitude. This might not sound too much, but it might be enough to induce tidal torque that that has a potential to slow down the rotation rate up to 5 days per million years, even in the prograde cases when they start the simulation. So an ocean could be also an explanation for the kind of slow rotation that we see today on Venus. It's one of those possibilities. So in the same order of magnitude as the atmosphere in some cases. So followed by this period, there was a day-side albedo feedback. And the slow rotation led in an early ocean strongly favored the vertical convection on the subsolar point, as you know, leading day-side high albedo clouds, less energy input into the climate system, and then you can have habitability or very temperate conditions at the surface if you condensate water in the first place. So you could have also a strong day-night circulation, which allows air to cool down in the night side via thermal radiation emission by opposition to the other model, where it says that there was no water condensation in the first place, so you don't have thermal escape on the night side. And I'm going to discuss that in a moment. But in this model, you assume that you have water condensation in the first place. So looking at the simulations that I'm going to present today, they are based at 2.9 billion years ago, where we have 1.47, the solar constant. And this temperate period might have lasted for a few billion years. We don't know exactly, even in this scenario, if we assume this habitability scenario. So there could be a carbon silicate in interior volatile cycles that could lead to climate stability, maybe plate tectonics. We don't know. Some studies point in that direction, others don't. But you probably don't need to have kind of tectonics on Earth to have some volatile circulation. So you probably could have CO2 could be retained in sinks, unlike N2, which continues to build up in the atmosphere. So you could have like a very at 2.9 billion years in this scenario, of course, an atmosphere which is 1 bar N2, and with a few trace amounts of CO2 that we consider here in this simulation. It's a possibility again. Then we consider that eventually some scenarios like multiple igneous provinces started to erupt at the same time on a very short geological time scale and drove the planet out of this climate stability where it was, and it passed a tipping point. And so what you have is that at the end, we have like multiple leaps erupting at the same time, lasting in between 10 to 100 million years. And there are some estimates concerning that. So we don't know actually how can this scenario could explain the entire quantity of CO2 in the atmosphere of Venus, but we know that it can explain a part of it. So it's very much an open question. And just for the discussion, we also have a possibility, speculative mechanism about carbonatite lavas, where you have like these discharge rates, and could that lead to a rapid formation of the CO2 atmosphere? I don't know. So that's a possibility. I don't think that anyone knows at the moment, but we see very long canals in Venus. So probably that could be the result of these flows that really lead to can be traced back to carbonatite lavas, which have high concentration of CO2. We don't know. It's an open question. And back again to compare the two models. So what we have on top is the model and the scenario that we are going through, which is a scenario where you have surface oceans, where we have a temperate water cool atmosphere in this case, where you have a very condensation in the substellar point. You have here the sunlight incoming, and you have a very high albedo clouds, which will prevent entry of some solar radiation into the climate system, and you can have efficient thermal cooling to space on the night side. So, of course, this is one theory and might be supported by some indications of recent of pH ratios and also other studies, but it really leaves a lot of open questions as well. The other possibility is the one that was explored by Martin Turbe in his study of 2021, where they say that water didn't condensate in the first place. So you could have efficient greenhouse effect by clouds on the night side, and you can have an efficient thermal, you can prevent thermal escape and cooling to space. on the night side. So you will have efficient absorption of sunlight in the sunlit atmosphere, and that could create a very entry point for energy into the climate system. But let's go first to the scenario that we are exploring and talking about today, where water condensated in the first place, and there were oceans forming on Venus. So we know that when we are talking about Venus and we are talking about a slow rotator, one of the things that are very much interesting, and Venus could be, of course, by many communities considered a natural laboratory for exoplanetary studies. So we know that some parameters are really important, like the meridional returning circulation and the kind of ocean heat transport that we are going to get. And these will respond to changes in the varying the rotation rate. Of course, these are very important. That's why we are also exploring the kind of ocean circulation that we have on this paleo-Venus, because this could be of interest also for the exoplanetary community, but because we have a laboratory and we are going to send missions there so we can study the atmospheric composition to look back to potential tracers of these ancient wet past. So the question here is, how was the ocean circulation in paleo-Venus, assuming the temperate climate evolution scenario in the first place? So we are going to use a full coupled dynamic ocean with 2000 orbits, and which until equilibrium is reached. And it's based on the runs of Genio 2020, which were extended, of course. And then we have here the horizontal resolution, land albedo, the kind of atmospheric levels, and the number of the layers in the ocean. And just to summarize, we will have a 310-meter depth ocean on Venus, which is equivalent to a global equivalent layer. And on the right, you see representation, and this already discussed today, which was the possible bathymetry and the possible kind of topographic rises that we see today on Venus. They might not have been there like 2.9 billion years ago. But for the sake of this exercise, we are going to assume they were. So we will have in blue the crustal plateaus where you have Aphrodite Terra and Ishtar Terra. And you will have in red, of course, the volcanic topographic rises, which in some cases they can be dominated by different kind of landforms, volcanic, rift, or coronae. So it's something that I'm not going to discuss here, but I'm happy to discuss afterwards. And we use these as input to the kind of topography and bathymetry that we are going to use in the model. So this is the Magellan data for topography, which has a resolution of roughly 4 kilometers. And what we have here is a conversion to topography and bathymetry, which are used as input in our model, ROCKE-3D. So, and these are the first results. In terms of the ocean surface, what we see on the plots on the top left is the sea surface temperature, and on the top right is the sea surface salinity, and on the bottom left, you see, on the left is the temperature, on the right is the salinity, and on the bottom left is the surface current speed modulus, and on the bottom right is the ocean mixed layer depth. So what you see, these are climate averages for 50 years, and you see an hotspot located here in the equatorial region. And of course, you might be tempted to think this is instantaneous. You see the solar point there, and that's not the case because remember, this is a 50-year average. So you will have, this is the result of a climatology, not just an instant in time. So you see the sea surface salinity also, and you see a very interesting dichotomy here in between the two hemispheres. You see exactly that. You see a much lower salinity in the northern and in the equatorial region, and you see a much higher salinity in the southern ocean. So what you see here is a surface distribution of salinity. And of course, in these regions where it's not plotted on the map because the scale and the values really go down, you see the river runoff. So what explains this in the equatorial region and in this lower salinity is the river. It's a combination of precipitation and river runoff, which tends in this model to favor a northward distribution outflow of the rivers. So for the surface currents, you see here in this plot that you have surface current located at the equator, and you have a contribution eastward of it that it's going to feed here the circulation in the equatorial region. And you see in the other side of the planet, in the other hemisphere, you see a kind of equatorward surface circulation in this hemisphere. But this requires further exploration, so we are still analyzing this data. As for the ocean mixed layer depth, we see, of course, higher, larger, thicker mixed layer depths in the polar regions, but located in the eastern ocean margins. So they are located just offshore of Ishtar Terra, if you are familiar with Venus, and they are located here in the just south of the Beta Atlantis region, in the just south of Themis region. And we want to explore here with more detail the ocean circulation, and this is what I just said in the previous slide. You see an equatorial prograde jet because Venus is retrograde in this case in respect to the Earth, and you see that this equatorial prograde jet is going to be fed by this circulation here at the surface. And you see an average equatorial motion in the other side of the planet. So this is a very interesting scenario because I've also explored that, and in some cases the surface circulation doesn't match really well the wind circulation at the surface in some cases. But I think that overall this is a good depiction of what we are getting coupled with the atmosphere. As for the equatorial jet, we see here plots of in the left of the zonal current speed in colors, and you see on the right east-west heat flux for both for the longitude of 75 degrees west for a latitude interval in between -10 and 10 degrees, and you clearly see that we would expect, in comparison with Earth, the appearance of an undercurrent at the equator. But here this is not really clear, so the simulations really don't suggest that. So we see a prograde circulation towards the west here in the surface, and you see eastward circulation in depth. Just below here, what is plotted here is the mixed layer depth, which is represented here for these latitudes in both slides. And you see, of course, isopycnals represented here by the darker blue lines. This is not rather familiar with what we expect to obtain with respect to the Earth, but what we see at the surface is an equatorial jet that's moving westwards, and we see an undercurrent that is moving eastwards. And we can also explore the kind of waves that we are going to expect in these oceans. So wave propagation in the equatorial region is at 2 degrees north of the zonal component of the surface ocean current. And you see an Moller plot here for the zonal perturbation. And you clearly see that the period of this wave is approximately half the rotation period. You see also this wave propagated here in the Venus orbits here on the x-axis, and in the y-axis you see the depth. And you see that this signal really tends to fade as we go in depth. So at the mixed layer depth for this location at 75 degrees west is around 100 meters. And you see in C an instantaneous field of this zonal propagation. So clearly what we see, and this is just an example of what the model is capable to explore, is the kind of waves that we are going to analyze in future work. And then in trying to vary also the rotation speed, it will be an interesting exercise as well. For the ocean mixed layer depth, as I said, we want to understand what is the location and what would be the depth and thickness of this layer. So what we actually see is that in the eastern margin of these oceans, just offshore of Ishtar Terra, we see really deep mixed layers that are going to change and do, they're going to change either energy and with the atmosphere. So this is a very interesting point to explore. And we see also in the Southern Ocean also the very deep mixed layers, which are deeper than 200 meters here on the plot. This is rather interesting, so it's something that we are going to explore also into future work. And just to continue, for the most interesting part, for the zonal average, we will try to make sense of the kind of circulation that we are getting for this shallow ocean, because it's so shallow. Again, it's just 310 meters depth. So what we see here is the surface temperature, and we see here the salinity, the potential density, and we see here the meridional stream function, the overturning circulation. So, of course, we are going to expect warmer temperatures, potential temperatures at the surface and in the equatorial region. So far, so good. But the signal of the salinity is rather intriguing because we see, of course, what we see in the surface, less saltier ocean at the surface for the southern and equatorial for the northern, in the equatorial region, and much saltier ocean for the southern ocean. So what we see here is that this distribution is not very easy to explain. We see that the salinity will increase in depth for the northern hemisphere, and we see that the salinity also increases in depth, but it stays really higher in the southern hemisphere compared to the northern one. And so the potential density is reflecting, of course, the salinity signal, and this is what we get, less potential density of the surface. It rather increases very dramatically in the northern hemisphere, and it increases, of course, in the southern hemisphere, but overall, the density is higher in the southern hemisphere. So we need to understand what is happening in terms of the meridional circulation, and this is what we propose in terms of the interpretation that we have here. So for the surface circulation, you will have an equatorward flow with a return at 200 meters. So we will see equatorward motion here, at both in the southern and in the northern hemisphere. And in these cells here, because red represents clockwise and blue represents anti-clockwise motion, we see in the northern hemisphere the formation of deep water. So this will lead to the formation of very dense, high saline water at depth. So this is what we actually see here. And interestingly, in the southern hemisphere, we don't see that. We see actually the model suggests upwelling towards the southern pole. So in the southern hemisphere, we see actually an outcrop, an upwelling of dense water that we see here in the south polar region. And the upwelling explains really the density or the kind of pattern and signal that we see here, where saline water is going to be displaced towards the surface and is allowed to reach the surface. And then again, the dense water is going to be redistributed equatorward at the surface. And you have here what we call also a return flow. So this is very interesting because even in a shallow ocean, we can have a very complex meridional overturning circulation with implications for the climatology. So I just want to comment just a few lines in terms of the aquaplanet simulations. Of course, we don't see here the impact of the continental configuration, and we see a surface temperature that is rather distributed in a very expected pattern when you see higher values in the equatorial region and a much lower salinity in the equatorial region compared to the poles because of the precipitation. And we see a westward jet that is related, of course, with the kind of circulation that we would expect for this planet, and a much shallower mixed layer depth. So the continental configuration that we see on the ocean circulation for the paleo-Venus does really has an impact on the kind of thickness of this layer, which is, of course, higher in the polar regions, but much higher because of the continents. So the conclusions and the next steps. The continental configuration allows for the development of an equatorial hotspot and a sea surface salinity dichotomy and an equatorial jet. We saw the development of the mixed layer depth that reaches the ocean floor at eastern margins of high latitude seas, and we see development of a complex meridional overturning circulation. This is rather important and interesting to explore for the exoplanet community. So the threats to explore, we would like to explore what would be the impact of the Ekman layer, trying to see how the model responds and trying to do some theoretical calculations. This is something that I'm already being done. And we're also going to explore a deeper ocean on the paleo-Venus. So some studies suggest that we might have a deeper ocean or the initial water reservoir was larger, because why not? We don't know yet. So we are going to explore what would be the impact of having, for example, 1300 deep ocean on the paleo-Venus, and how does the mixed layer, the MOC, and the oceanographic parameters respond to a deeper ocean in a slow rotator? So what we have here is just a representation in figure 18 about what would be the topography after changing the sea level rise of about 1,000 meters with respect to the 310-meter global equivalent layer Venus. And as you can see, the kind of land area is much smaller, and so we will only be impacted by the main coastal plateaus of Ishtar and Aphrodite and some volcanic rises that belong to the Beta Atlas in this region. It is really interesting. So this is something that we also want to explore. And to finalize, we are going to explore the paleo-bathymetry and topography. This is something that was already discussed here today, and I'm open to discuss these either after the presentation or in private conversations, because we want to explore what would be a different bathymetry for Venus. We know that the topography is dynamic. Maybe some of these topographic prices weren't there at the beginning, and probably not at 2.9 billion years ago. So yeah, we are going to explore these and talk with some geodynamic guys to try to see if we can come up with good solutions for the kind of bathymetry that could serve as an input to the model. With that, and of course, we are going to explore the tidal dissipation on these oceans and trying to explore what would be the kind of ocean circulations. And with that, I conclude my presentation and thank you for your attention.
Thank you, Diogo. Any questions?
Yeah, I have a question, Diogo. Could you go back to your topography map with the ocean, like the salinity map that you have?
Yep, just one moment.
Yeah. Because the salinity difference between the north and the south is very interesting, right? And I'm just gonna stare at this for a second and see if I can.
Yes, please.
Yeah.
I need all the help.
We discussed that probably some of it's to do precipitation patterns and also
Yeah.
runoff in the continents.
Runoff, yeah.
That makes
north.
sense, but I was also wondering if in the south you get a bunch of sea ice, and that is that
Not much sea
not
ice.
much sea ice?
Yeah,
Not
you
much,
could have
yeah.
some brine ejection.
Yeah,
in the ocean.
yeah. And then also if you go to the zonal cross section,
Yeah.
you have the kind of you have like a ridge underneath it look like that's yes, and that the
Yes.
bottom
Symmetry.
yeah, so that ridge is certainly affecting it, right? Because it can't outflow, so
It's just like the Sicily Straits that separate the eastern and western Mediterranean Sea.
yeah. But why is it getting concentrated there? That's interesting.
That's something that we are going to explore definitely. Yeah, it's intriguing.
You don't get I guess you don't get sea ice in the I guess the insulation.
There's not much sea ice
Yeah.
in each round.
So these simulations are 4x5
Yes,
resolution.
these are all 4x5.
I was just wondering, it looks like it's extremely low actually resolution for such kind of the ocean. In some places you probably have just one or two cells, and you have a strait so there could be like significant boundary condition effect just because we have how to say it, like our ocean boundaries.
Yeah, we could run this at higher resolution to see if we see any differences. We have 1 by 1 degree resolution in the maps, so we could.
Yeah, because you could just basically slow your motion through those straits just because of artifacts of the algorithm that your shores are kind of like non-smooth.
I mean, this is very different from Earth, right? You have all these low latitude continents which you don't have, and and you can see the ocean looks completely different.
And the ocean salinity is initialized with Earth values.
35 psi.
But is it constant at the beginning of the run, or
it's constant throughout the entire ocean? 35.
Okay.
Yeah, go ahead, Rory.
Great talk, Diogo. I was curious about on the next slide. I think maybe you said this and I just missed it, but I was confused about the overturning between the two hemispheres. Yeah, so in that middle panel, I mean, it kind of looks like on the southern hemisphere, it looks normal. Like on the surface, it's flowing to the equator, and then there's at depth, it's flowing back. But then on the northern hemisphere, it looks like everything is flowing to the equator at all depths. Am I missing something here? Maybe you explained this. I'm sorry, but I'm just wondering, am I understanding that right, or is there something really weird?
Thank you for your question. I mean, I'm just missing here an arrow indicating that you have a return circulation at 200 meters. I spoke about that, but it's an arrow missing there. Probably I should include it for verification purposes.
Okay, good. Thank you.
But you have a return here, and so what you have here is clockwise motion. So this is anti-clockwise. You have a return here at 200 meters. So you have formation of deep water at close to the North Pole. Mm-hmm.
Conserve the water.
Yeah, well, yeah, I was hoping we conserve the water.
Yeah, Diogo's doing his PhD with João Duarte, who's a geodynamicist in Lisbon, and Matthias Green is a co-advisor who many of us know. So he's working with top-notch people on very fun stuff. And I also thought that next picture where you made the ocean depth much deeper kind of ties into what we were talking about with Linda earlier. Maybe the one more was it? Yeah, this one on the lower right.
Yeah, this one.
This is what I was saying before. You have these volcanic rises and stuff, and this may be like, I mean, if you believe this plutonic squishy lid is like the early Archean, this might be exactly what you would see, which would be really cool.
Yeah,
We have the data of a world that is actually like Earth, which Mars is not.
Exactly, because you have that dichotomy between hemispheres. So and probably you'd see like these proto-continents like Ishtar and Aphrodite just wandering there, and that would be very similar to early Earth, I think.
Yeah, that is. Okay, great. Thank you so much, Diogo. Let's move on to.
Thank you for having me.
Thank you. Let's move on to our next talk. Sophie, are you there? Sophie's in Bangor, Wales. She works with Matthias Green, and she's going to talk about a project we've been working on for, I don't know, a couple of years now.
Yeah, it's taken a lot longer than we were initially hoping. Yeah. So I'm going to talk about the ocean circulation of a future supercontinent, and this was actually born out of a project I'm working on with Mike and Matthias, who was just mentioned, and Anya, who's a PhD student on the project, looking at the climate drivers of Archean Earth. However, we're going to go into the future as a means of exploring the impact of sort of a different continental configuration on the ocean circulation. And this work builds on Mike's 2021 paper, which looked at the sort of, I guess, more surface and atmospheric climate of a host of different future supercontinent arrangements. So just to give you a bit of background information, so Earth's continents undergo these so-called supercontinent cycles. So basically they gather into supercontinents every 400 to 600 million years. And this image on the right-hand side gives you a bit of an overview of the past supercontinents that may have existed. So the most recent one would have been Pangaea around sort of 300 million years ago, which was a supercontinent that extended basically sort of as a sort of a long drawn out meridional supercontinent. And then as we go back in time, we have Rodinia and Columbia, and I guess those things become more uncertain as we go back in time. The next supercontinent is expected to form around 200 to 250 million years into the future. And there's a number of different scenarios that have been sort of identified. And we have, I'll just sort of briefly introduce them. We have Pangaea Ultima, which again, which is an equatorial supercontinent. We have Orica, really rather similar, also an equatorial supercontinent. We have Novo Pangaea, which has a bit more of a sort of more meridional extent, and then we have Amasia, which is essentially a polar supercontinent. But in this work, we're going to focus on the equatorial supercontinent Orica. And the work that's been carried out so far has basically mainly looked at sort of habitability of these future supercontinents, has investigated surface climate conditions, and atmospheric circulation. So the bottom figures from Mike's paper showing sea ice concentrations, and the top paper comes from the Farnsworth et al. 2023 paper. And the latter paper focused mainly on looking at habitability from the sort of perspective of for mammals, essentially. So it got one of the earlier talk, wet bulb temperatures were mentioned. So essentially for this supercontinent setup, it looks like with increased sort of orbital parameters which we'd expect in the future, large parts of the sort of equatorial region may become uninhabitable in the sort of range that we would expect for mammals today. However, so far, nobody's really looked at the oceans and ocean circulations. And if we look back in geological history, we know that the oceans were actually really rather crucial for life on Earth. And if we look at events such as mass extinctions, many of them at least had a strong contribution from the ocean, if not were mainly driven by oceanic extinction. So it appears that going back in time, it's not necessarily the surface climate that's just the simple driver of habitability, but it's also the conditions in the oceans that are very important. So here I'm going to be talking about two different simulations which we carried out with the 4x5 degree setup of ROCKE-3D. So on the right hand side you can see the Orica topography and bathymetry, and you can see that essentially we have, oops, sorry, I'll go back one. We essentially have this equatorial supercontinent. We have very slightly more land mass in the northern hemisphere than we do in the southern hemisphere, which becomes kind of important later on. And then we have this this ridge feature in the sort of to the west of the continent. And I'm going to be talking about two different simulations. So we have we call it, I'm going to call it PD Orica, so it's present day Orica. So it's Orica topography with here, but with present day orbital forcing. So we've essentially got the same day length as today, and we've got the same installation values as today. And then F Orica, so future Orica, is again the same topography, but with future orbital forcing, which is an increase in day length by half an hour and a 2.6% increase in installation with respect to present day. So you can see that those are really rather small changes in orbital forcing. The F Orica simulation is essentially one of the same simulations that Mike presented in his 2021 paper, but basically both simulations were run for 5 or 7,000 years respectively, until the deep ocean was in equilibrium, and we were quite surprised how long this took to actually spin up the model until it was actually in a stable state. The aim of these simulations is to sort of test the impact of these rather small changes in orbital forcing on the ocean circulation and climate. So if we just have a very brief look at the surface climate. So on the left we have the PD Orica simulations, and on the right we have the F Orica simulations. And then on the very right hand panel we have the zonal means of the top here is sea surface temperature, and in the lower panel we have ocean ice fraction here. So firstly, if we look at the global mean surface temperatures, we can see PD Orica has got a mean temperature of 16.3 degrees, and F Orica has a surface temperature of 20.7 degrees, which is a 4.4 degree difference, which is quite large for the relatively small changes in orbital forcing that we're experiencing. And you can see here, if you look at the zonal means of the sea surface temperature, they increase at all latitudes, but if you have a closer look, you can see that the increase in F Aurica is slightly larger in the northern hemisphere than it is in the southern hemisphere, which is driven by the larger landmass that we have in the northern hemisphere. And that becomes important later on when we're talking about atmospheric circulation here. And if you look at the ice cover in the bottom panel, you can see that we're shifting from a state in PD Aurica where we have ice cover that extends sort of into the sort of subpolar latitude, or well, sort of, yeah, subpolar latitudes, whereas in the F Aurica we've shifted to a near ice-free state here, with ice only small ice fractions occurring very close to the poles. So essentially we sort of flipped from a ice present state to an ice-free state. Now, if we look at ocean circulation, we can see some really rather pronounced changes. So the top panel here shows the meridional overturning circulation, and red colours indicate a clockwise circulation, and blue colours an anti-clockwise simulation. So that's the same plot as sort of same principle as Diogo showed earlier on. So in PD Aurica, we have really rather sluggish circulation in the centre or the sort of deep parts of the ocean. So you can see here surface gyre systems, which we would expect as normal. So got subtropical gyre, subpolar gyre here. And then we can see some degree, a relatively weak degree of deep water formation at the poles in both latitudes, in both hemispheres here. However, now if we look at the F Aurica simulation, the picture looks completely different. So now this is much more a picture that we would expect in the present day ocean, so where we have deep water formation in the North Atlantic, and also to a much lesser degree in the Southern Ocean around Antarctica. So essentially we're switching from a state where we have a mainly gyre dominated circulation to a strong and active meridional overturning circulation. And then if we look at the heat reports in the bottom panel here, you can see that overall, so this is the total atmosphere and ocean heat transport together. You can see that global total doesn't really change that much, but if we look at the ocean, it looks it looks quite different. So we have the F Aurica, which is plotted in red. Case has a much stronger northward heat transport, especially in the northern hemisphere, whereas the southward heat transport is somewhat reduced. And then in the atmosphere, yeah, changes are rather small. So the question is a bit, why is this? So if we now have a look at some other measures in the ocean, so we can start thinking about, well, where does deep water actually form? So in PD Aurica, as we saw for the meridional slices, you can see that deep water formation here takes place at the polar latitude, as far north and as far south as you can go. And then you can also see that the gyre systems, which is essentially located in these regions here, sort of have a deeper mixed layer as well. In contrast, in F Aurica, you can see that the mixed layer depth is deepest in the sort of, well, subpolar latitudes here, especially in the sort of around a band of a sort of 60 degrees north, and then to a lesser degree in the southern hemisphere as well. My mouse keeps disappearing. Okay, here, yeah, so you can see the equivalent in the southern hemisphere. But if you see in the zonal mean, there's the deepest this location with the deepest mixed layer depth in this case occurs around 60 degrees north. Now, very interestingly, if we're looking at surface density, the locations where deep water forms correspond with the latitudinal maxima in the surface density. So for PD Orica, we have the highest density latitudinally at the poles. However, if you slightly difficult to distinguish in these colors here, but you can see it's this little blip here. We basically have a latitudinal maxima in sea surface densities around 60 degrees north. Now, what's causing this? So if we, going back to the salinity plot that we had beforehand, if you have a look at this, you can't really see, nothing's, in fact, the temperatures here are relatively warm. So if we have a look at the sea surface salinities, you can see that they drastically differ between these two cases. In the PD Orica case, we have relatively low salinities in these subpolar latitudes, whereas in the F Orica case, we have this band of really quite high salinities that occur in these regions. You also see higher salinities in these mid-latitude areas here. So the question is, what actually drives these salinity changes? And we basically have sort of two candidates, I guess. We have, is it atmospheric processes? So in this case, it would be, is it sort of the changes in evaporation and precipitation patterns? Or is it oceanic processes that drive salinity? So that would be essentially the transport of salt by ocean currents. So I'm going to start with atmospheric processes here. And this top panel here shows the atmospheric stream function. Now, originally, we didn't really expect with those relatively small orbital changes to see much of a shift in the sort of atmospheric circulation patterns. However, that wasn't quite true. So in red, we have the F Orica, the future Orica simulation, and in blue, the PD Orica simulation. And now what I want to draw your attention to is the shift in these two thick lines, which essentially show the location of the rising limb of the Hadley cell. And you can see that they have, in F Orica, it's essentially shifted approximately yeah, but I think it's about 4 to 5 degrees northwards. And that's because the strongest warming of the surface is essentially shifted into the northern hemisphere, which then alters the location of the rising limb of the Hadley cell. You can also see that, oh, I can't see my mouse again. Yeah, you can see that all the other the sort of the downward limbs here have also shifted polewards in both the southern hemisphere and the northern hemisphere, with the longer day length. So that, in consequence, is going to change the evaporation precipitation patterns, which are shown in the next panel down here. And so by eye, it's quite hard to identify the differences. So that's why I plotted down here the change in evaporation precipitation. So that's F Orica minus PD Orica. So that means, so red colors here indicate that with the future orbital forcing, it's got drier. So that would mean it would be a more saline surface ocean, and blue colors indicate that it's got wetter. So you can see that the poles here, the polar areas here get wetter in the F Orica simulation, but the mid-latitudes tend to get more fresher. However, if we now look at the sea surface salinity differences, so again, it's F Orica minus PD Orica, you can see that whilst overall, if we sort of, I don't know, squint a little bit, the mid-latitudes have got more saline and the poles have got wetter. Actually, these two patterns don't really correspond that much at all. And we have this huge increase in salinity around the area where we form deep water in F Orica, but not in PD Orica. So essentially, we can say that, yes, we have a change in the atmospheric circulation, and that affects the precipitation and evaporation pattern, but we can't really fully explain the salinity differences by this. So let's have a look at atmosphere-ocean changes. So the shift in the atmospheric circulation cells, which I showed you up here, also leads to a change in the surface wind patterns. So on the left panel, we have the U winds, west-east winds, and then on the right panel, we have the meridional, so north-south winds. And here you can see that because the circulation cells have shifted, that's also led to a shift in the locations of the peak wind speeds, especially in the sort of mid to high or mid to sort of subpolar latitudes. And because the ocean gyres are wind driven, that we can also, as a consequence of that, see changes in the ocean horizontal stream function. So that's your gyre circulation. So again, red colours indicate a clockwise circulation, and blue colours indicate an anti-clockwise circulation. And again, it's quite hard to exactly make out the individual changes here. So I've plotted the zonal means of this, and again you can see that in essence the location of the peak circulation, the peak stream function, has shifted very slightly polewards in both hemispheres. So you can see it here and you can see it here. So that indicates that in F Orica, these circulation systems have just shifted slightly further polewards. And that, in consequence, changes the salt transport in the ocean as well. And here you can see, and this is because we have very slightly more landmass in the northern hemisphere, these changes are more pronounced in the northern hemisphere. And that means that we're transporting more salt polewards in the northern hemisphere than we are in the southern hemisphere. So essentially, so we can say that sort of the poleward shift in the peak surface winds changes the wind-driven gyre circulation, and that in turn changes the northward transport of salt. So just to sort of quickly summarize this. So essentially we have a poleward shift in the atmospheric circulation cells, that then is more pronounced in the northern hemisphere because we have an unequal land distribution, which leads to an unequal degree of heating. And then this change in the atmospheric circulation cell, in consequence, alters the precipitation and evaporation patterns, and we get drier mid-latitudes and a saltier surface ocean, and that in turn leads to a change in location. And then furthermore, we have a change in the location of the peak wind surface stresses, which then alter the wind-driven gyres, and that in turn changes the northward transport of salt in the southern hemisphere. So in essence, both atmosphere and ocean processes and their interactions are important in driving the shifts in the in the location of the deep water formation. So just to conclude, so we can see that really rather small changes in orbital forcing can lead to quite profound changes in the ocean circulation. And so we basically need to look at processes both in the atmosphere and the ocean in order to explain why that is happening. And also we can see that they interact with each other, and we can see that the salinity distribution in this case is really quite important. And this is interesting because that's slightly different from, for example, a present day case where interactions with sea ice become really quite important in driving the location of deep water formation, and losses in heat to the atmosphere actually crucial in increasing the density of the water such that it becomes dense enough to allow convection to occur. So we're in a different system. We're in a salinity dominated system here rather than in a temperature dominated system. And as ocean circulation is well, strongly affects ocean ventilation and the oxygenation of the ocean, these sort of processes potentially have implications for sort of sustaining life in the oceans. And we also have learned that fully sort of resolving ocean dynamics is actually really important to understand all of the processes that are going on in the ocean. And just to sort of give you a sort of small outlook of what we're going to be working on next. So the next part of this work is going to be looking at how changes in tidal mixing in response to the change in land distribution might affect the ocean circulation of the future supercontinent. So thank you.
Okay. Sophie, any questions? Okay, Rory, go for it.
Maybe I've missed this, but was this for zero eccentricity orbit?
No, this is modern obliquity.
Or sorry, I said eccentricity, I think.
Eccentricity, sorry, it's modern.
Modern.
That kit stays modern. Only thing that changed here was the day length and the insulation.
Yeah, because I was just wondering, you know, I mean, over time, right, the eccentricity there goes up to 0.12 or thereabouts.
This is only 250 million years in the future, so it won't change by it.
Well, but that cycles over 100,000 year time scale.
Right.
So it's interesting to think about like on Milankovitch time scales that you would get different eccentricities. So I was just kind of curious if you've thought about that in the future, looked at that at all.
No, I haven't so far. So I think it'd be something to explore. It's another parameter that we could look at in this whole sort of system and explore how that affects. Yeah, I mean, we know going back in sort of, well, I know last few hundred, throughout the Pleistocene, we know that that's had a huge impact on ocean circulation. And again, we know from that there might have been flips in the ocean circulation state with a modern Earth continental configuration. So we know that there's probably a bistable regime in sort of in the present day continental configuration. And potentially we also we've got some other simulations where we can see that there's potential to form deep water in the Pacific as well. So it looks like for the same continental configuration, there's the potential that we have several different ocean circulation states.
Great, thanks.
And the obliquity was kept the same.
Obliquity and eccentricity kept the same between both.
Sophie, Tony, you said you looked at both atmosphere and ocean processes. Have you looked at the impact of sea ice on the salinity distribution between your runs? Because the brine rejection actually would have quite a big impact on the formation of bottom water.
Yeah, I mean, I guess ultimately because there's so little, I mean, if we look back at because there's so little sea ice in this case, in the F Orica case, where we form deep water in the sort of subpolar latitude around 60 degrees, to me, it looks like the brine rejection has very little impact there because we have so little sea ice. And I guess, interestingly, in the paleo-Orica case, we form deep water right at the poles, again, away from the areas where we have where we'd expect to have brine rejection. To me, it looks like sea ice has a rather small effect in this case, and a much smaller case than we have in the present day Earth, where we do form deep water close to the sea ice edge.
These were done using Planet 1 or Planet 2?
Planet 1, but not with the updated brine rejections.
Yeah, so in Planet 2 you have a more sophisticated brine rejection scheme. Could be interesting to check.
Well, we can apply it to these. We can just extend these with the brine rejection scheme.
Yep.
Yeah, that'd be super interesting. Yeah.
They might be very different, but I hope not. Yeah, sure, Chris, go ahead.
Yeah, so, hi, Sophie, good talk. So you're spent a lot of time comparing F Orica to PD Orica, but if you were to compare F Orica to present day continents, I mean, you were interested in ocean habitability in the future. I was just interested in, kind of like the spatial extent of, say, upwelling zones where you'd have nutrient supply, how that might compare to the modern day. And just in terms of like habitats where you'd expect phytoplankton and that sort of thing relative to present day.
Yeah, I haven't looked into that so far, but again, that'd be something that'd be really interesting to do. Yeah, this is really rather recent, so we're sort of still working on this, and it's still got potential to be extended. So I mean, I guess you'd expect some of the upwelling zones again to be sort of along the edges of where you have the gyre systems. I guess you sort of, depending on, I guess the sort of present day equivalent of the Southern Ocean might be very interesting as well. You'll have upwelling there. So yeah, I don't know. Great question. I something to look into next as well.
But we have some simulations because we have done similar experiments with modern day continental configuration. It's just that they're still running and they take time to analyze. So it's coming. We have like, I don't know, 2 or 3 papers in theory in the pipe with all these simulations. So
yeah, probably at least.
time to papers, do the analysis.
Yeah.
And they did take a long time to come into equilibrium, as you said, 5,000, 7,000 years. It takes a long time because they're deep. It takes a long time for the whole ocean to come into equilibrium. The temperatures and standardly stabilize. I mean, probably not surprising, right? Earth climate models take time to change, of course. Okay, great. I think that's about right on time, Sophie. Thank you so much. And now we're going to move over. Yeah. And thank you both, Sophie and Diogo, for sticking it out for so long, because I know it's late for you all. So really appreciate that. If you can stop sharing. Oh, there we go. We got it. Tony's going. All right, Tony, you're up.
All right. So I just wanted to give you first a quick update on all the exciting things coming to the ocean and the sea ice in ROCKE-3D over the next few weeks, months, years. And then I'll give you an overview of our Icy Moon project. So as Kostas explained yesterday, the parent model of ROCKE-3D is Model-E. And here I just wanted to show off our brand new logo for Model-E at the top left, although it doesn't have any meat on top of
There's no
we don't have
tenderloin
the
steak in the.
I'll send you the gift. We can use it next time.
Although the NASA logo is called the meatball.
It is called a meatball.
See?
Good point.
So Planet 2.0, as described by Kostas yesterday, is based on Model-E 2.1, which is the version we use for our latest IPCC submission. But since then, we've been working on a few different versions of Model-E, E3, E3.1, E3.2, and even E4. And we're working parallel on a few different versions of the model because some features take more time to implement than others. But obviously, they will give birth to Planet 3.0 and Planet 4.0 in the next few years. There are features that are very specific to the ocean in ROCKE-3D. I'll talk about this a bit later.
One thing, I think that E3 is over. I think nobody works there anymore.
Oh yeah, so the E3.1
and further.
That would be the next committed version of the model. And I put in a title of this slide, Model-E toward ROCKE-3D, but it should go both ways because you always find bug pushing the advantage of ROCKE-3D is you pushing the model in some extreme situation that we're not doing in Model-E, and you find some bugs. I found some long-standing bugs in the ocean, diffusion subroutine that probably have been in Modeli for 10, 15 years. And so you're able to fix them in the ROCKE-3D and then port them back to Modeli. You also have some features that are original to ROCKE-3D, like the coupling with Socrates that are now being tested into with the Earth model in Modeli. And so starting with the ocean, one of the big focus going from E2.1 forward will be on the structure and resolution of the horizontal grid. Most of the work has been done by Max Kelly. First, the horizontal grid. Up until now, we were using lat-long grids, which are very easy to use, but they come with two big singularities at both poles. So going forward, we'll be able to use a cube sphere where you're projecting your sphere on a cube, and you're removing the singularities the big singularities at the pole, and you're replacing them with smaller singularities at the corner of your cube, which are much easier to treat. The horizontal resolution, it's also one of the big push going forward. Up until E2.1 and Planet 2.0, we were using ocean resolution going from 4 by 5 degrees to 1 by 1.25 degrees. In E4, you'll be able to go down to 1/8 of a degree, keeping in mind the CPU cost of it. But that also required some updates to the way the ocean is parallelized. Up until now, you would be limited by the number of latitude cells that you have in the latitude direction. Now you can use thousands of processors to run the ocean.
What's the resolution of the ocean for the cube sphere 1 by 1? Maybe you said it, and
yeah,
I didn't hear
it. For which one?
Cube sphere 1 by 1.
You'd be able to choose your resolution. That's actually an example of an E4 run that Max did a few months ago. That's a coupled run. The atmosphere is on the cube sphere. So it's a 1 degree resolution. The ocean is 1/8 of a degree. In this case, it's a lat long grid with a 40 level, and you can see the.
Wait. Step back. You said atmosphere is cube sphere and ocean is lat long?
Yep. In this particular configuration. But you'll also be able to run the ocean with the cube sphere. So
that's interesting.
But you can see the amazing level of detail that's the velocity field on the left, the surface, and the SST on the right.
And how long did this run?
I'm coming to that.
Yeah. And how many thousands of processors did you use?
Just
that's why my jobs don't go into Discover now for the past
amazing twist and turn in the Gulf Stream and all these mesoscalities that we couldn't resolve.
Pretty amazing.
No, coming to your question, Rory, how many million years you said earlier this morning you were getting?
It takes 5 minutes to do 1 million years.
Okay, so I think if I remember correctly, this run on 500 cores, and you get a modular a day. A day with 500 cores. So you always keep in mind
using lat long for the ocean. If you go to cube sphere,
it would probably be faster.
Yeah. Oh, yeah. I guess you could spread it out more. Yeah.
Right. Always keep in.
Tony, does that mean that we're going back to like one simulation for the institute at a time?
At least for the next few years.
Yeah.
We will have
the DOE computers.
We'll have one resolution. And then everyone will be able to access the data from this. But it's not like everyone will be or will want to run 1/8 of a degree. But it's great to know that we have the capabilities that some other models have had for a few years. And not everyone should run 1/8 of a degree. It really depends on your use case scenario. Most people for ROCKE-3D will still want to stick to our workhorse 4 by 5 degrees, or maybe the 2 by 2.5. But
I guess my question was more along the lines of, if there is something running at 1/8 of a degree, is anyone else going to be able to get time on the machine, or is it just going to be that?
Hopefully we would get some priority, some section of Discover kept, or maybe that's a use case for, I know that Amazon wanted us to try their cloud computing. Igor has been running so some version of Model.
Well, as long as you have resources, of course you can run them.
So
we can also use Pleiades, but it's also busy.
But they're used to having much bigger jobs because they run these big cosmology codes and stuff there. So they're probably used to people having thousands of CPUs in allocation for a single
So I
job.
think, either Max or Larissa will run a long integration, but just to get the ocean in equilibrium we will need to be very careful about what kind of resource we're using.
You could run for 2 or 3 years, right? Someone's going to be around to analyze the data then.
Someone's going to be around. This place exists by the time it comes to equilibrium.
If you want 2,000 years to equilibrate, 1 day per year, 6 years.
We should start. Maybe we start Max to. We should tell Max to start now.
Our Mars
CPUs will change twice during that time.
as slow as
But they're dry.
Yeah.
Right. This is the ocean has to come into equilibrium.
Yeah, of course.
The land planet, the equilibrium.
But in terms of model performance, I mean, it's nearly the same thing.
Yeah. But we don't have an ocean.
And even if you include CPU increasing, maybe GPU, I don't know.
I don't think you can do that in GPU.
Yeah,
we're not
programming
GPUs.
We'll see. Okay, so switching to the CIs, one of the big thing coming to Model E as of E3.1 would be the switch of the CIS thermodynamics from the atmosphere grid to the ocean grid. So that gives a better coupling.
3.1.
E3.1, yeah. 3.1. That gives a better coupling between the ocean and the CIs, but also since the ocean is usually at a higher resolution than the atmosphere, you'd have a higher resolution immediately for the CIs. We have a new radiative transfer model that's based on zone hygiene, offline radiative transfer. We've already implemented for the bare CIs. It used to be only based on the CIs thickness, and now it's also based on the temperature, the salinity, and the air content of the ice. We just received funding, map proposal from last year to do the same thing for the snow, sitting on top of the sea ice. Speaking of the snow, up until E3.1, we'll have 4 distinct snow model in Model E. So that there's the snow sitting on top of the sea ice, there's the snow sitting on top of the land ice, glaciers, and we're pushing toward unifying all these snow models toward one. Then we'll roll them all, which is Igor's snow model.
Which is obsolete, of course. Because the one I'm using for Mars is it's significantly different.
But this is going in 3.1 also, this unified snow model. This obsolete unified snow model is going in 3.1.
So far, that's what people are using. But
okay,
hopefully
so it's working.
But hopefully we are.
Yeah, hopefully it will be easy switch to new.
To exotic.
Yeah, exotic.
Oh, so you do plan to put that in?
Well, eventually, yes.
Sure. I don't know if it's just our baby or if you're going to share your toys with other people.
Well, maybe that can be the Europe putting back toward Model E. Maybe later.
Yeah, that's great.
And right now the ice arrays are shared over land and ocean, right? Is that disentangled in E3?
Which arrays?
So like you'll have like sea ice or thickness things like over land.
Yeah, when you're plotting the diagnostics, when you look on the land, it's actually the lake ice. That's what you're plotting. If you see any value on land, it will be the
like
lake
ZSI, CIC.
Yeah, ZSI and OISFR.
Present over land.
These are only for lake ice. And there will also be some improved parameterization for the lateral melt of the sea ice and the roughness of the sea ice.
Sorry, did we change the diagnostics or add new ones or?
No, so it's always been the case that the ice fraction, OISFR, for example, these are both. If it's on the ocean, it's a sea ice. If it's on land, it's a lake ice.
Right.
And I was saying that there are some ROCKE-3D specific features for the ocean. Starting, we were talking about it a bit earlier in your case with aquaplanets, where we're still forced to use a land point at the South Pole. We are working with Aerosols on bringing the same treatment of the ocean dynamics that we have at the North Pole to the South Pole. Historically, it was developed on Earth, and because of Antarctica, there was never a need for a treatment at the South Pole. So it's a bit time consuming, but we're working on this, and it's a very selfish reason because we need that for our deep ocean Europa simulation. And speaking of that, I'm switching to the second part of the presentation about our icy moons and deep ocean project. By deep ocean, we mean tens to hundreds of kilometers, and basically we're trying to have a model of the ocean, the subsurface ocean of an icy moon like Europa or Enceladus in our solar system, under thick ice shell. And by thick ice shell, we mean tens of kilometers. I think we think Europa has an ocean of around 100 kilometers of depth, and the ice shell maybe around 40 kilometers on top of this ocean. You have the schematic view of the thick ice shell sitting on top of the ocean, and sometimes, if you're lucky, you can see this water escaping in space. We discovered that with Enceladus first, but we can see it also on Europa. And I remind you that in 16 days and probably 4 hours now, the Europa Clipper is still on target for an October 10th launch. Orbit insertion is for in the Jupiter system. It's planned for 2030. So I think we still have 6 years until people can tell us that our simulations are totally wrong.
You gotta get this working before then.
It's already working pretty well in 2024. So to do that, first starting with the ice shell, we don't have the rheology, the sea ice rheology to model 10-kilometer thick ice shell. So basically, we decided to use the surface pressure array as a boundary condition for the ocean. At the top of the ocean, we basically calculating what will be the pressure at the bottom of a 10-kilometer thick ice shell, and we use that as a boundary condition.
Can I ask something?
Yeah.
Do you expect that the ice will be sitting on top of the water and pressing it? Or do you expect some kind of voids because of the difference of pressure when the water is between 0 and 4 degrees Celsius?
We think, talking about the temperature, the ocean probably has this temperature freezing at the bottom of the ice shell. But yeah, we expect no cavity between we think like maybe there's some atmosphere between the ocean.
No, not atmosphere. I'm just saying that since the shell is so thick, like tens of kilometers, it might develop in a way that it is so hard, and then the ocean inside might shrink a little bit and just create voids, you know. Even a meter of a void, it means 0 pressure from the ice. That's a huge difference.
It's an interesting question, but so far we've only considered a case where there's no void between actually we impose on the first cell at the top that the temperature of the water is the temperature of freezing water at the bottom of the sea ice, which is for this kind of pressure around -3 degrees Celsius.
Okay, so the water is already expanding in that temperature.
Yeah.
So if there was any void at 4, then it will probably go away. Okay, never mind.
I guess it would be similar question, like to ask her about just general planet, like if there is any void between, I don't know, core and the mantle, or mantle and.
Yeah, but we don't model those.
Yeah, but I don't think there are any voids.
It would really need a very stiff shell.
Remember that the shell,
everything is stiff on rocky planet.
Yeah,
remember that
ice is not is
Ice is much softer than.
Much softer than.
Well, there are many phases of ice.
Than
Yeah,
Some of them
lithosphere.
are very
and
hard.
the pressure of ice down there might make it funny, yeah.
And remember that the ice shell is free floating because it's not attached to the floor. It's kind of free floating.
Well, you don't know that. Maybe
we
there's a mountain someplace that is buried. You don't know that.
well, yeah. We think that's what's happening. But yeah, until Europa Clipper gives us a better idea of the interior of the moon, we will. That's the fun of it. You can assume different scenarios and explore.
I don't think anybody is modeling with some kind of mountain.
No, I don't think so. But
So far.
Okay, so second thing, 2 years ago, I rewrote the hydrostatic ocean to be a quasi-hydrostatic ocean. I think I presented before the equations of a quasi-hydrostatic ocean dynamics, so I won't torture you with the equations, but basically you have to establish a few terms that were neglected for Earth, because these are good assumptions to neglect them for Earth, and you have a full treatment of the Coriolis force and the relaxation of the shallow water approximation. We extended the lookup table for the equation of states for oceans deeper than Earth. We're using geothermal heating at the bottom of the ocean that was developed by Rito really to simulate the injection of heat at the bottom. Something I want to do next is to do the same thing, adding a source term in the ice shell at the top of the ocean, because you have some heat coming from the flexing of the ice shell at the top of the ocean. I wrote a variable gravity field scheme. On Earth, the ocean, let's say on average, is 5 kilometers deep. So it's very thin, very shallow when compared to the radius of Earth, which is 6,300 kilometers. On a planetary body like let's say Enceladus, which is around 250 kilometers in radius, a third of the radius of the ocean. So you can consider the gravity at the top of the ocean to be the same as the one of the ocean. So now we can have a gravity that depends on the depth of the ocean. We're planning to include Gary's tide model. And we also can play with the ice shell geometry. So if you, for example, on Enceladus, we think that the ice shell is thicker in the northern hemisphere than in the southern hemisphere. So you can play with the shape of the ice shell and see how that impacts the general circulation of the ocean. And so when you put these ingredients together, I'm just going to show you a run. After my talk, we have a Kaushal, who's been working with us for a year now, I think, with John Marshall at MIT, who's also working on the Icy Moons project. Probably will dive deeper, sorry for the pun, but in these simulations. But basically, I'm going to show you a run with an ocean depth of 60 kilometers, with a 15-kilometer ice shell sitting on top of it. You have geothermal heating. We increased. We think that on Europa it's closer to 0.1, but just to generate some ocean circulation a bit faster, we increased it to 10 water per meter square at the bottom of the ocean. So in this case, we have both poles have a land point. We had to include a land point at the North Pole as well for symmetry reason. We ran this for 20,000 orbits. So Europa orbits Jupiter in around 3.5 days. So 100 orbits is roughly equivalent to an Earth year. So every frame in the animation, you're going to see averaged over 100 orbits, and there are 16 frames per second. So these are the zonal averages for the temperature field, and UV and W are the three components of the velocity field. So these are zonal average. You have the depth on the Y axis with a 0 at the top and 60 kilometers at the bottom, and you have the latitude from -90 to +90 on the x-axis. So I'm just gonna launch. Hopefully it works. Yeah. And so yeah, we're gonna reach 20,000 years, reaching some kind of equilibrium state after 20,000 plus orbits. And you can see that we have two distinct regions. For example, if you look at the temperature field, an equatorial region which has a lower temperature than this higher latitude. And so we can look at this using what's called the tangent cylinder. It's just geometric feature. Imagine a cylinder that has the same axis as your icy moon, and the surface of the cylinder is tangent to the bottom of the ocean. So you have these red lines that are tangent at the equator here. You can calculate this angle here, which is the angle between the equator and the tangent intersecting the top of the ocean. And if you plug the values for Europa, you come with an angle of 16 degrees. And yeah, so this tangent cylinder separates the ocean into two distinct regions. You have one portion of the ocean which is inside the tangent cylinder, and another portion of the ocean that's sitting outside of the tangent cylinder. And so if you go from spherical coordinates on the left to our model, which is now vertical coordinates, then, for example, this point here that intersects the ocean surface will become this point here. This point at the equator at the bottom become this point here, and this one will be this one. So this straight line in spherical coordinates becomes more like a U or V line in our vertical coordinate system. And if you plot a tangent cylinder of 16 degrees for our Europa case, and if we relaunch the movies, you can see that roughly it separates the border between these two different regions. But once again, Kaushal will probably go back more into this in the next 30 minutes.
Yeah,
I'm almost done. Okay. If you look at exactly the same fields, but from above, we were looking at the, I think that, yeah, that's the bottom at 59 kilometers. If I relaunch these runs, you can see a rich eddy field redistributing the energy horizontally, but you see this feature at both poles, which are basically due to the presence of the land points. And it's almost like if you were running your ocean in a channel and you have a wall on each side of the ocean. So we already have the option of removing the North Pole land points, but we're working right now with Gary on removing the southern land points. And that would be available as well to everyone who wants to run an exoplanet or a planet that doesn't have a continent at the South Pole. So we started with Europa, but we're planning to study other subsurface ocean like the one on Enceladus, but that also can be applied. I think maybe there's a TRAPPIST planet that has it's an atmosphere, a rocky world, but with a deep ocean. I don't remember which one.
Possible.
Yeah, possible. And I'm currently writing this paper, like basically a summary of all the modification we needed to make to go from ROCKE-3D to something that's able to simulate the subsurface ocean of icy moons. And that's it.
Thank you. Okay. Any questions?
Yeah, Tony, have you folks talked to Christine McCarthy at Lamont at all?
No, I know the name, but I don't think I met.
We
Christine
talked,
before.
I talked to her a long time ago. We had a telecon when Caleb had that climate school thing or whatever. We had one conversation with her and blah, 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 but then.
Yeah.
Is she working on the same?
Well, she works on material properties of things like ice shells
Yeah.
of icy moons, which, you know, might be
Yeah, yeah.
useful for, you know, working out how you want to define your ice shell properties and what that does to the tidal heating and stuff like that accordingly.
Maybe if you can put us in touch, that would be
Sure.
I mean,
Right.
we have a lot of other things to do before that,
I
but
know,
down the
I-
road, definitely.
So initially, when we started the project, I think it was in 2021, that we thought we would be able to use the ice rheology of modeling, but we quickly realized that we had to go the way of the surface pressure array. Then we always think that there will be a next phase where we'll be able to bring in. There are some ice model with a rheology that allows for tens of kilometers of ice. So that would be the next phase of the project to get something a bit more realistic.
Can you very quickly replay page 14?
Which one? This one?
Not this
14.
14.
14.
You're in 19.
Up.
This one.
Yeah.
Yeah, can you play the video? So, and
Full screen.
okay, so on the top right.
Yep.
Essentially, this means that you have two equatorial flows, that one goes one direction, the other goes the other direction, right?
Yep.
I get that right?
Yep.
Okay.
And there's some kind of oscillation going from one side of the equator to the other. The other seems more stable. But yeah, the zonal component of the velocity field.
Okay, so is this a feature that is generated because you just provide too much heat that
We won't
goes
have time to answer this. We have to move on to the next talk.
Let's get to Kaushal for the next two.
Yes, okay, stop sharing, let Kaushal share. Okay, Kaushal is gonna continue in some ways from what Tony just did. So Kaushal, please take it away. And unmute yourself, young man.
Hi, am I audible?
You are audible.
And do you guys see my screen?
Yes, everything's good.
All right, so let's begin. I am very happy that I'm following Tony because he gave a very nice prelude to the results that I'm going to present here. For the past 1 year, I've been working in collaboration with my postdoc advisor, John Marshall, and members of the ROCKE-3D team, including Igor, Max, Tony, Gary, Michael, on the Icy Moon project. And for this talk, I'll be focusing on dynamics of the moon, of Jupiter's moon, Europa. So as you can tell by now, Europa is an icy moon that is orbiting the planet Jupiter. And as Tony mentioned, we suspect that this icy moon has an ocean that is at least a few tens of kilometers deep, if not over 100 kilometers deep. This makes it a promising candidate for detecting extraterrestrial life within our solar system. And it is also the target for the upcoming Europa Clipper mission that launches next month and is expected to arrive to its destination shortly after. We only have to wait 6 years until it gets to Jupiter. Rory had mentioned that these ice-covered moons are deep, but I hope that this figure offers some more perspective regarding what it actually means. So what I've done here is that I've scaled the radial distance between the surface of the ocean to the center of the celestial body, which are Earth, Europa, and Enceladus in this case, to 1. And we see from the panel on our left that the ocean on Earth is like a thin film at best, but the ocean on Europa and Enceladus are much deeper. In fact, they occupy up to 8% and 16% of this radial distance, which we have scaled to 1. Note that the outer shell of this two spheres that I'm showing is the surface of the ocean, which is in contact with the bottom of the ice. So I've not shown you the ice shell that encases these oceans here. Because of this, we need to relax the shallow water approximation, and the dynamics are essentially non-hydrostatic. Both the ocean on Europa and Enceladus are expected to be geothermally heated, and the tangent cylinder, which is a cylinder that encases the core here and is aligned along the axis of rotation, is expected to play a key role in the sense that it would bifurcate the dynamics into two regimes. One would be considered inside the tangent cylinder, and the other would be outside the tangent cylinder. When I use the word the core of the moon, I mean anything that is below the seafloor. Previous studies have shown that the convection in these icy moons is expected to be aligned along the axis of rotation when you're inside the tangent cylinder, and perpendicular to the axis of rotation when you're outside the tangent cylinder, which would give rise to a subtle equator to pole temperature gradient. The circulation also moves heat away from the equator, which would support the subtle temperature gradient. And a typical layer in the ocean would look something like this. The dashed lines that you see on the panel in the middle and the panel on your right-hand side is the point where the tangent cylinder intersects the surface, which is the surface of the ocean, not the surface of the celestial body. I would also like to mention that this is not the distribution of the geothermal heating, but think of it as a representation of what the horizontal temperature would look like in a typical layer in the ocean. For the subsequent part of the talk, we'll only discuss Europa. And the equator to pole temperature gradient that you see on Europa is unlike anything else that we see on Earth, because the tropical regions on Earth are much warmer than the poles. But on Europa, this is sort of inverted. The equator is cooler than the poles. But remember that this ocean is also encased inside an ice shell. So we expect surface to seafloor temperature gradients to exist as well. The ocean is bounded inside this thin, hollow region that you see, which is between the two spheres that I've shown on your figure. And I've sort of enlarged this small region in the ocean in the sub-panel. Since the ocean is being geothermally heated, we expect the water at the bottom of the ocean to be warmer than the water near the surface, which is a recipe for convection, but we'll get to that. The model that I'm using right now has a horizontal resolution of approximately 100 kilometers at the equator. This is the 4x5 degrees lat-long resolution of the ROCKE-3D. The ocean is bifurcated into 35 vertical levels and spans a depth of 60 kilometers. we are using a nearly uniform geothermal heating flux. Right now, we have chosen the geothermal heating flux to be 10. I'm talking about the mean, but we are carrying out multiple simulations for different values of geothermal heating. And we expect to identify a general trend that we can extrapolate to lower values of geothermal heating, which are much more relevant to Europa and also Enceladus. The sea surface temperature is restored to the freezing temperature right below the ice shell in the top layer. And the salinity is held constant. Now that we have a basic understanding of the setup, let's see what these interesting temperature gradients that have been going on and on about tell about the dynamics. So the surface to seafloor temperature gradient is a recipe for perpetual convection, which is very nicely captured in the figure that you see on the right-hand side of your screen. In this figure, I'm plotting the zonally averaged latitude depth distribution of n squared. N squared is the square of the Brunt-Wasserloff frequency, which quantifies the stratification in the ocean. As you can see, n squared is proportional to the vertical gradient of density. And for positive values of n squared, the stratification is stable, but for negative values of n squared, the stratification is unstable. So you can see that everywhere in the ocean, the stratification is unstable, and wherever it is stable, that stability is also very weak. This by itself is a very interesting feature, but remember that the horizontal temperature gradients in our ice-covered ocean are expected to be opposite of what we see on planet Earth. So we expect to see warmer waters in the mid-latitude and colder waters at the low latitude. And I think this question was asked in the previous talk that is the zonal flow in any way related to these temperature gradients? And the answer is yes. Because we have a horizontal temperature gradient, we get a vertical shear, which is shown in the figure on the right-hand side. The relationship between horizontal temperature gradients and vertical shear is often called the thermal wind balance. And we also observe this in Earth's atmosphere. But remember that on the Earth, the air is warmer at the equator, but cooler in the mid-latitudes, which is why we get winds going from easterlies at the surface to westerlies at the high latitude. On an ice-covered moon, the horizontal temperature gradients are reversed. We have warmer water in the mid-latitudes and colder water in the low latitudes, which is why we see westerly currents at the surface and easterly currents near the seafloor. Wherever we have horizontal temperature gradients, we can always explore the possibility of seeing baroclinic instabilities. And this is true for ice-covered moons as well. This equator to pole temperature gradient in our setup gives rise to baroclinic instability. And near the surface, these eddies move heat from the mid-latitudinal region to the low latitudes. And I'm going to show just that. So the two spheres that you see on the left-hand side of the panel are the horizontal temperature fields, a movie of the horizontal temperature fields. And panel A shows the temperature fields at a depth of 4 kilometers, and panel B shows horizontal temperature field, the latitude longitude distribution of the temperature fields at a depth of 56 kilometers. We see these rich eddies embedded in an easterly flow. And recall that the flow was easterly in a large part of the ocean and westerly only near the seafloor. So even at a depth of 56 kilometers, you see easterly flows. So what are we doing next? So I'm working on developing an analytic framework to understand the temperature field, the velocity field, and the overturning circulation in terms of two key non-dimensional numbers that you see on the screen. The term eta is dependent on the geometry of the tangent cylinder. Here, Ri is the radius of the core, and h is the depth of the ocean, and R naught star, which is dependent on the geothermal heating flux and the rotation rate of the celestial body. The question that we're hoping to address is to identify what is the role of the advective and eddy components of the meridional oceanic heat transport in terms of these key non-dimensional numbers. And because we are carrying out simulations for different values of Q, which is our geothermal heating flux, we are hoping to identify some relationships which we can extrapolate to values of geothermal heating which are relevant to what is expected to be on Europa and Enceladus. On the development front, as Tony mentioned, we are working towards implementing gradients in the thickness of ice, also tides, and all this would give more insights into the different mixing mechanisms that we expect to observe on these ice-covered moons. And the overarching goal of my work here at MIT is going to be to obtain some insights which could help us better understand the transport of biosignatures from the seafloor to the surface on these icy moons. That's it. Thank you so much.
Thank you, Kaushal. Any questions?
Yes.
Yes, go for it.
For the thickness of ice, that you will have a gradient. Both you and Tony mentioned it, so I don't know who is going to answer this. I wonder, this already happens on Earth, but of course in a far smaller extent, right? So is the extra development needed that you have to take into account the movement of ice like a land glacier on Earth, or it is because it will be heavier and it will go deeper into the ocean or something else?
Yeah. Basically, since we're only using the pressure, surface pressure array in the first phase of the project as a boundary condition, it's just relates to the amount of pressure you're applying to which part of the ocean. But you can think of right now it's constant in time, but you can have it evolve with time. So if you want to simulate some change over time of the thickness gradient, you could do that easily as well.
And the reason why we want to do that is because the change in the freezing temperature of ice is a function of the thickness of the ice shelf. So it's not ice shelf, the whatever sort of ice there is on these ice-covered moons. So, and the gradients in the thickness can be of the order of the thickness of the ice shell itself. So, for example, on Europa, the ice shell can vary from between, let's say, 10 kilometers to 15 kilometers from pole to equator. So that because the temperature gradients that we expect on these ice-covered moons are so small, it is important to account for these subtle variations in the freezing temperature, which would happen due to change in the thickness of the ice. So the movie that you see on your screen, if you note the difference between the maximum and the minimum temperature, it's less than 0.1 degrees centigrade. This is the potential temperature. So, which is why it is an important component of properly understanding the dynamics on these.
The thickness of the Europa ice shell is not really well constrained right now. We don't really have, we can estimate it, but Enceladus, we have a better idea. So for example, on Enceladus, it's thicker in the northern hemisphere and then thinning down to I think around 3 kilometers at the South Pole, and that's the region where you see these geysers of water spewing into space directly. So probably because the ice shell is much thinner, the weather has a better pathways to
But isn't there a negative feedback that is counterintuitive in my mind there? You don't develop the ice shell from the above, right? You develop it from below, of course. So if you have a thick ice shell, well, it's not an ice shell. If you have a thick ice, it is heavier, so it increases the pressure, so it makes the water less susceptible to freeze.
Yes.
So it is not developing extra.
So right. Basically, we're starting or run in what we think is thermal, because there's no atmosphere on Europa. On said the ice shell is a result of the thermal equilibrium between space, which is very. We think that there might be a tiny atmosphere at the surface of the ice shell, but it's basically super cold at the surface, and you have liquid water, and the existence of the liquid water is due to these moons orbiting giant planets like Jupiter or
so it's literally
Saturn.
moving the ice.
Yeah, and
from tides and
it goes back to this talk yesterday where I was thinking when we were looking at the inhabitable zone shifting toward the outside of the sun. So let's imagine, I don't remember, maybe it was in the beginning year when the plot was showing that Jupiter was going to be in habitable. So what will happen to the surface of an icy moon? Like, it's probably going to start melting from the top. There would be a new equilibrium for, I don't know how long it will stay in this region. So
well, there's no sublime.
It doesn't have an
Besides,
besides
that, we expect, because there is slight eccentricity to the orbit of these icy moons, we expect the action of tides to also be relevant. And as I showed in my figures, that there is a component of advective heat transport and eddy-driven heat transport. So with the change in the thickness of the ocean, you're basically changing the geometry of the ice shell. So and the dynamics would also change. So the distribution of heat, which is coming in from the geothermal heating, would also change. That in turn feeds back into what the equilibrium thickness of the ice shell would be. So there's no reason to expect it to be absolutely uniform. And it's very difficult to constrain what the thickness would be without actually making some measurement. They expect ice shell in Europa to be thinner at the equator or at the poles. At the poles.
Europa Clipper will give us some constraints.
Yep.
It's one of its jobs.
6 years.
In 6 years. Well, it's going to get there before juice, and that's all that matters.
Yeah. We expect the ice shell to be thicker at the equator, right?
Yeah. Well, let's say that after the launch, we will. Yes. The launch can always be postponed by.
That's true.
So it will take 6 years to go. But
it's flying straight there on
right.
SpaceX Falcon Heavy.
And it needs to decelerate at some point, right? So it might be doing some orbits that are not very useful.
Yeah, and remember,
it's going to end up in the system before JUICE, because JUICE has to do all these gravity assists to get up there still. It isn't even left in the solar system, and it launched over a year ago.
So remember, it won't be orbiting Europa because of the huge amount of radiation that Jupiter is emitting in the whole Jovian system.
Okay, so
it's gonna go toward Europa, then and there are, I think, 100 orbits already programmed, but it has to get back outside of the influence of the radiation belt of Jupiter, and then come back to Europa, do another series of measures, and then
just to protect itself.
Yeah, there's not enough shielding provided to keep it orbiting Europa constantly.
Oh, and Steve corrected me.
Only done
Mars, Earth, gravity assist. Yeah, okay. Sorry?
There's another question in the chat. Have you only done simulations so far with a uniform surface pressure boundary condition, or would a lower pressure at the poles drastically alter the circulation? Yes, gradient in ice thickness, which would result in a gradient in pressure, can have a completely different dynamics, and we are hoping that we'll be able to address this in the coming few years.
Okay. Any other questions? All right.
Are you using
Steven?
Gibbs? See what? I am not sure which equation of state is this one in particular, but we're using, I think, UNESCO 84 equation of state.
Okay,
Yeah,
but it's basically a seawater equation of state, right?
Yes.
Okay.
In the next few phases of the project, we're gonna try, probably based on some of your papers, Steve, so some different equation of states for model.
Cool. Yeah, sounds good. Yeah, I'm presenting some new equation of state stuff. We're putting into Planet Profile at AGU, so maybe if folks will be there, I'd be happy to discuss then.
Yeah. I do plan to be on at AGU. Steve.
Great, let's meet up. Sounds good.
Sure. Absolutely.
Excellent.
Hi, everyone.
Hey, Steve. Thanks for joining.
Thanks for inviting me.
See you in a couple weeks. All right. Shall we take a break? Yes. 20 minutes. We kissed Tony and Kaushal in a little early. We got lucky there. Okay. Take a break then. Okay. We have two more talks today, and these are Venus-related talks. And one is by Arnaud Salvador, who's going to talk to us about the early evolution of terrestrial planets, and especially Venus, or related to a review paper that we worked on almost 2 years ago when we started. Anyway, take it away, Arnaud, and unmute yourself.
Yes. Can you all guys hear me and see my slides?
You see presenter mode, just so you know.
Oh, okay.
Swap displays, yeah.
That, yeah.
Perfect. Awesome.
Great. All right. Well, thank you, Michael, for having me here. And so, yeah, this is going to be a presentation about a review paper that we've been working on for a little while with a bunch of people here. It has now just been published. It will soon be published as a book as part of the EC collection, and it's also available in Space Science Reviews. So yeah, Venus, early evolution and potential habitability. Let's start with a few definitions, context to clarify and make it all clear. I'm going to talk about early magma oceans, and this can be defined as a substantial portion of the planetary mantle that is molten in the early history, and this differs from the steady state magma oceans, such as lava worlds, for instance. And then I'm also going to distinguish the early versus the long-term evolution of the planet. For that, the early evolution will be focusing on the phase of the evolution where the heat from the planetary interior has not yet been evacuated, compared to the long-term evolution where the climate and the surface conditions are controlled not by the heat coming from the planetary interior, but rather from the stellar flux. All right. Oops, sorry. We'll talk also about habitability, so we'll just stick to the common definition, that is the ability to sustain liquid water at the surface of a rocky planet. And this, of course, primarily depends on temperature and water vapor pressure. And here, just with these two factors, it highlights the importance of energy, which is, again, either the heat from the star, or for the early evolution, the energy of the system is dominated by the heat coming from the planetary interior, and also the atmospheric composition that basically controls how this heat is redistributed through the absorption of gas species, and also their evolution, of course. So let's start with that. These two pictures, and just define a bit of context here. I'm sure you are all familiar with this, but it's always good to start with it. So basically, we have these two planets, the Earth and Venus, that are very similar in terms of bulk properties, in terms of size, mass, and then density, which indicates that they most likely have a similar composition and possibly a similar interior structure. So it indicates that they're made of the same material, and they probably have a common past, or at least in terms of building blocks that made them. Yet, as of today, they have opposite surface conditions, where the Earth, of course, is nice and cool, where we have temperate surface conditions, liquid water, and 1 bar atmosphere, mostly made of nitrogen and oxygen, while on Venus, it's very hot, of course, super dry, and there's a lot of CO2 in the atmosphere. So if those two planets had a common origin, they probably had a divergent evolution. So this is what we're going to try to understand, how, starting from a common past, these two planets became so different. So let's start with the beginning, the planetary accretion. So how planets form. The theory indicates that planetary systems originate from gravitational collapse of molecular clouds, where giant planets form earlier than rocky planets close from the star. And so it seems that Venus and Earth accreted in the same region of the disk from similar material. And there's two main outcomes of the planetary accretion. First, because the planet, when the planets grow, there's a substantial heat accreted by the planet. And this is due to several factors. So there's impact heating. When you have two bodies that collide together, you have a substantial heat generated. You also have radiogenic heating of short-lived radioactive elements, and also viscous dissipation during metal silicate separation, when the planet interior differentiate into different layers. And the combination of these heat sources is thought to result in an early global molten stage, where you have a magma ocean layer, so a layer of lava basically around the planet. Also, another outcome of the accretion stage is that it seems that a substantial amount of volatile species has already been accreted once the planet have reached their about final mass. And so out of that, if we start with this phase where we have a magma ocean, where a significant part of the planet is molten, how do we evolve from that phase to something that is more like today, where the mantle is solidified and the volatiles has been distributed between the different envelopes? So this magma ocean phase is really important because of the low viscosity of the magma, elements can travel throughout the planetary mantle, the planetary interior, more easily than today. So the timescales are very different. So during this phase, it's also likely that most of the metal silicate separation occurs and that the core is formed. And again, the volatile species are distributed between the different planetary reservoirs, and thus the atmosphere is formed. What facilitates the exchanges between the interior and the atmosphere is that there's no strong or long-lasting boundary between the interior and the atmosphere. So you have both efficient volatile transfer, but also efficient heat transfer between the interior and the atmosphere of the planet. Then it's also a coupled system. So the magma ocean outgassing forms the atmosphere, and then the thermal blanketing of the atmosphere buffers the heat escape to space, and maintains and slows down the cooling of the magma ocean. And so the surface temperature and the atmospheric partial pressure are set by the magma ocean solidification. So this has been well studied in the past decades, with more interests recently. So one important thing is that the magma ocean cooling, because of this absence of boundary layers between the interior and the atmosphere, it truly sets the surface conditions for the long-term evolution of the planet. And we will see what are the processes that are involved and how they effectively change the picture and the long-term evolution of the planet. So in general, how do we model the magma ocean phase? We start with an hypothetical initial state where we have a fully molten mantle. We generally assume that the core is already formed, and we simulate the last magma ocean event. So the volatiles are initially supposed to be dissolved within the molten mantle, so within the lava. And we also assume that there is no atmosphere because for a giant impact to melt the entire mantle, it is assumed that the atmosphere would also be eroded through the impact. Then out of this initial state, we model the cooling and crystallization of the interior, the exolution and degassing of the volatile. So I'll describe this in more details, and that form the atmosphere. And at the end, we have this sort of final state, basically, where we transition to something different, the long-term evolution of the planet, where we have an atmosphere, a solid state mantle. That might not be the case necessarily. We also have simulations where the planet, which is maintains a part of the surface molten, but in general, we have a solid state mantle at the end of the simulations. The volatiles have been outgassed to the atmosphere, and then we are asking the question whether or not we have habitable surface conditions and if a water ocean can be maintained at the surface of those planets. So out of the surface conditions, surface pressure and temperature that control the existence of liquid water at the surface, we can also constrain the magma ocean duration that controls the timing of the first solid surface, and then also the onset of the solid state mantle convection or the geodynamic regime, whether we have subduction, plate tectonics, or stagnant lead. This sort of early evolution modeling also constrained the solidified mantle water content that also influences the geodynamic regime, and of course the composition and properties of the atmosphere. This has also, of course, implications for the characterization of exoplanets. So how do we proceed? In general, we have two distinct reservoirs. We have a planetary interior that is modeled like that it's kind of a box model. So we have the convection, and we compute the flux that is evacuated from the magma ocean by convection through generally parameterized convection laws. We generally assume that we have a bottom-up solidification of the magma ocean. So initially we have a fully molten mantle, and then the solidification proceeds from the base of the mantle up to the surface. And then we have heat transfer at the surface of the planet and degassing that forms the atmosphere. And out of the atmosphere, we compute its structure and the amount of flux that is able to be radiated by the planet. So there's this heat flux equilibrium that controls how the system cools down. That is written here, where you have the heat flux that is evacuated by the planet at the top of the atmosphere equals the sum of the heat fluxes of the system, the convective flux coming from the mantle, the planetary interior, but also the flux that is absorbed by the planet at the top of the atmosphere. And again, when we have a magma ocean phase, we can distinguish these two, or for the early evolution in general, we have this phase here where the heat coming from the magma is so important that it totally overpowered the heat coming from the star, or the flux coming from the star. So the first phase of the evolution is really controlled by the evacuation of the convective flux from the magma ocean. And then once this flux becomes negligible, the surface conditions are controlled by the flux that is absorbed at the top of the atmosphere, and then by the stellar flux more generally. So we have these two phases, the early phase where we have a rapid cooling, a vigorous mantle convection, and the surface conditions that are controlled by the convective flux from the mantle. And in this phase, we have a strong mantle degassing. And this phase ends the end of rapid cooling stage, basically, where we assume that, or we consider it's just an arbitrary criterion to define the end of this phase, but basically this end of the rapid cooling stage is defined when the convective flux becomes an order of magnitude lower than the absorbed flux. So basically negligible compared to the flux absorbed from the star. And then we have a second phase where that is rather the long-term evolution of the planet, where we have slow cooling if we still have some heat to be evacuated from the interior, solid state mantle convection, the surface conditions that are controlled and driven by the flux absorbed from the sun, and it's a much more steady state. And again, we're asking here the questions about the surface conditions that are reached at the end of the rapid cooling stage. So the magma ocean thermal evolution and crystallization sequence look like that. As I was saying, we generally assume that initially we have a totally molten stage where the entire mantle is molten. And then the solidification occurs from the base of the magma ocean to the top. So we have crystals that accumulate basically. And in this orange part, the behavior is, the connectivity of the crystal is different. And then the motion are slowed down basically because of the connectivity of the crystals that does not allow for a liquid behavior as we have in this red region here, which is really like lava basically. So here we have, during the evolution, we have different phases and we have a part of the mantle that is controlled by the viscosity of the crystals and a part of the mantle that is controlled by the viscosity of the metal. How it looks like when we have the temperature as a function of time, and in blue we have the surface temperature of the planet, and in red the potential temperature of the planet, and here you have a sketch of the interior structure and how basically it crystallizes with time. So you have a strong decrease of the temperature because of the convection happening in the magma ocean, and you have this solidification from bottom up. Then for Venus in the Earth, let's say we want to model what's the influence of the distance from the star, because Venus is closer from the star than the Earth. So we can think about starting with the same planet, the exact same planet, the exact same volatile content and composition, and just change the distance from the star. It has been done by Arnaud et al. In 2013, where they basically demonstrated that if a planet, if a planet is at the distance of Venus, it would be in equilibrium with its stellar flux and maintain a molten surface at the end of the rapid cooling stage. While if the planet is further away from the star, like the Earth, it would be able to form a water ocean at the end of the rapid cooling stage. So out of that, we can define two types of planets, depending on the distance from the star. If you're close from the star, you have slow cooling planets, and basically those planets will stay molten for longer and then will lose their water through atmospheric escape on the long term. And then out of further away from a critical distance, you have type 1 planets like the Earth, where you have a flux from the star that is low enough for planets to cool down faster and be in equilibrium with their star at a state where they're able to form water ocean. But this is mainly due to the fact that these atmospheres are dominated by water. And water, if it's the only species in the atmosphere, depending on the location from the star, we will have these two distinct and kind of extreme stages. And this can be explained by this, by the famous runaway greenhouse that is basically illustrated here. So if we plot the heat flux as a function of the surface temperature, and so you start the magma ocean cooling here from the right-hand side of the plot. So you start with a high heat flux that is coming from the planetary interior, and then you decrease your flux because you cool down the planet, basically. If you are close from the star, you will basically reach an equilibrium with your stellar flux at surface temperatures that are above the silicate melting point here with the red crosses. But if you are slightly further away from the star, you will have a strong transition here, a big gap between surface conditions where you can have a water ocean at the surface of the planet and a surface that stays molten. And this is because we can think about this problem inversing the situation. Let's say we start with the Earth right now and we increase the stellar flux, let's say. Then we will start vaporizing the ocean, and then we will saturate the atmosphere with the ocean, with water that will enhance the greenhouse warming, that will end up evaporating the whole ocean, that will generate a very strong greenhouse effect that will be able to, and we will be able to reach thermal equilibrium and evacuate fluxes out of the atmosphere at surface conditions that are much that are associated with much higher temperature. So here we approach the system from high fluxes, high heat to possibly lower heat fluxes. But then, what if we consider alternative atmospheric composition? We know that Venus atmosphere is CO2 dominated. The Earth was also most likely rich in CO2 before it has been trapped in carbonates. So it seems realistic to assume that those planets, even at the inner edge of the habitable zone, had a lot of CO2 in their atmosphere. And so if we do so, this strong transition between what is called type 1 planets, where you can form a water ocean, to type 2 planets, where you have a molten surface, is basically not that steep, and you can have additional stable surface conditions where the heat flux you receive from the star, where basically the planet is at radiative equilibrium with the flux received from the star, and you can have this third type of planet here where you have solid surface without a water ocean. So now let's dig into more details regarding the outgassing, because we talked about CO2 and H2O, but how are those species, how do they end up in the atmosphere, basically? So initially, and how do we model that? So initially, again, we assume that the volatiles are dissolved within the melt. So we have a total amount of volatiles here, let's say here H2O. And then the volatiles are distributed between the different reservoirs. So some of the water through hydrogen might be incorporated into the metallic core. Then you have some incorporation of water or CO2 into mineral phases, and this is controlled via partition coefficient and interstitial trapping. Then you can also partition your volatiles between the melt and the gas phase. This is called the exsolution, when you basically take the gas, the volatiles out of the solution, which here is the melt, and then you form gas bubbles at low pressures. This is controlled by the solubility laws. A good example of that is catastrophic outgassing event here, where basically where you just open a can of soda. Initially, you have all the volatiles that are dissolved within your solution here, and then once you open the can, you have a decrease of pressure, and the volatiles can basically go out of the melt and form gas bubbles because they are not maintained under high pressure into the melt phase. So for that, it's important to realize that volatile outgassing and the exsolution of volatiles from being dissolved in the melt phase to the gas phase occurs at low pressure. And then after that, once you have the gas bubbles that are formed, those bubbles need to reach the surface of the planet before being re-entrained by convective currents to be finally outgassed and then form the atmosphere. We'll also discuss the fact that because volatiles are incompatible species, they preferentially stay into the melt rather than going to the crystals. So when you solidify the magma ocean, you tend to increase the concentration of volatiles into the melt. That also favors their exsolution. So when we talk about degassing, we really talk about the way volatiles are transferred from the lava to the melt. Sorry. From the melt to the gas phase, and then to the gas, and then once they're in the gas phase, excuse me.
In about 5 minutes, Arnaud.
Oh, okay. Once they're in the gas phase, how they reach the atmosphere. So I'll just skip that a bit. Okay, so as I mentioned, basically you have to have the volatiles reach low pressure, so that they can go out of the melt into the gas phase. And when you do so, you have a very efficient outgassing. In general, people assume that because you have strong convective currents, all the melt reaches low pressure fast enough before the solidification of your magma ocean, so that all the volatile species are transferred into the gas phase. But we conducted some simulations where we simulated the convective dynamics of the magma ocean to try to constrain the influence of convective patterns on the amount of melt reaching the surface. And it turns out that in some cases, it takes some significant time for the entire melt to reach the surface and then outgas the volatiles. That could basically buffer and slow down your outgassing. So out of that, you can think about different scenarios of outgassing. You can have continuous outgassing with an atmosphere, a thick atmosphere that is formed. You can have catastrophic degassing, where you have only localized degassing, or you can also have minimal to no degassing. And out of that, here I mostly focused on the degassing part, but you have other processes such as cloud albedo fieldback that will control how fast and how much of the heat is transferred, is evacuated from the magma ocean, and the state you reach after this early evolution. So depending on the flux also you receive from the star, or the flux you absorb from the star, depending on your outgassing regime and the state of the atmosphere resulting from the outgassing of the magma ocean, you can have these different types of planets at the end of the rapid cooling stage. And from that, you have to branch out and model the long-term evolution with the different processes, such as cloud formation or hydrodynamic escape. And basically, we try to map out different ways to start from a magma ocean phase here to Venus or the Earth. The main conclusion of that is that we still have a lot to do, and basically out of that, the magma ocean itself could determine the long-term evolution of the planet, and hence the habitability or not of the planet. So I think I'll stop here, and I'm happy to discuss, for instance, many of the uncertainties. I haven't been a chance to touch base here, but we can discuss more. Thank you.
Thank you, Arnaud. So any questions? Oh, no. Right, the Harmano and Lebrun papers, they don't know where that critical line is, right? So that's the big quandary. And then they're using these steam CO2 atmospheres, which we don't even know if that's what they are, right?
Yeah. It's a big, and no clouds also are included. So if you have clouds, and depending on the location of the clouds, there's this Turbe paper, of course, that shows that if you have clouds on the night side, you would still end up the magma ocean phase with as a type 2 planet, so a molten surface, and then you keep all the water in the atmosphere, which is then sensitive to hydrodynamic escape, and so you end up losing all the water during the long-term evolution, and you end up having a Venus without having a habitable phase. Yeah.
Assuming there is water.
Assuming there is water, yeah, of course.
I mean, you know those experiments from Paolo Sossi. He's saying that the water is highly soluble in the melt, and that it's not going to come out, right? I think that's the big conclusion from his work. So it could be that we don't know. First of all, we don't know. It depends on how oxidizing the mantle is, what the atmosphere is, and then if the water is really so soluble in the melt, you could have 1,000 bar CO atmosphere, and we have no idea then how that really operates. And
yeah.
How do we get to water oceans to begin with, right? I mean, so the big mess.
The solubility is really an important point of that, and also those models only consider either the solubility of H2O or CO2, but actually the solubility of one species influences the solubility of the other. Basically, if you start forming bubbles of CO2, then you will have some diffusion of water that will go into these bubbles, and then you'll have the solubility is also affected by many parameters that are themselves unconstrained, and that depends on temperature, pressure, melt composition. Yeah, so there's a lot. Yeah.
I just have a silly question. I mean, we always talk about the outgassing of dissolved species, but pretty much. But are they maybe also chemically bound to stuff around, or is it always just dissolved? I mean, water and CO2. Do they exist like in CO2 or in water state all the time, or they actually chemically bound to some species and basically first have to some chemistry has to be involved before they separate? Do you know?
Depends on the species. For example, nitrogen doesn't sit.
Well, just water and CO2. I guess
that's ammonia. But yeah, Arnaud, go ahead. Sorry.
No worries. Yeah, so you can have. I mean, those species you can have a speciation of different speciation of those species. So you have really like C, carbon, hydrogen, oxygen, and then depending on the oxidation state, for instance, you could outgas methane instead of CO2 if you have a reduced mantle, especially at the top of the magma ocean where outgassing occurs. Then you have different ways to have those species. Either they can be incorporated into those minerals, into some minerals, or exist as themselves. There's plenty of ways, basically, and the models are in general focusing on one way or another. So there's definitely chemistry involved, but it's also something that we need to be better addressed. People in general just assume that there's a given amount of H2O and that it behaves in a certain way, but there's a lot that could be improved here.
Okay, thank you again, Arnaud. We're going to move on to our last talk. Thank you so much. So, Rakesh, are you there?
Yeah, I'm here. Can you hear me?
We hear you. It's good.
Hi, I'm right here. So
Okay,
yeah,
good.
I'll share my stuff in a moment here. Here we are.
Good job.
So, hello, everybody. I'm Rakesh Mogul. I work with Mike. I live out in California. I'm a professor at Cal Poly Pomona, and I'm here to talk to you about new interpretations of Pioneer Venus mass spectra, which is a much more simple title than what I submitted. So I want to at first just thank my collaborators, acknowledge them. Of course, Mike's one, Misha Zolotov, and Sanjay LeMay are my important collaborators. So this talk is about the Large Probe Neutral Mass Spectrometer, which is an instrument on board the Pioneer Venus Large Probe. and the large probe actually detached from the Pioneer Venus multi-probe in 1978. And this thing then dropped down to the surface of Venus in approximately 54-minute flight time when considering parachute deployment. Now, I know everyone knows Venus pretty well here, but we know that with altitude, temperature also increases as you go towards the surface, and that becomes important in this talk in a little bit. So as this space probe, or as the Pioneer Venus Large Probe dropped toward the surface, the LMS started atmospheric gas collection about 64 kilometers. But what happened is really interesting here, and it's actually central to this talk, is that the LMS, the Large Probe Neutral Mass Spectrometer, experienced a temporary clogs of the inlets approximately between approximately 50 and 25 kilometers. But at 25 kilometers or so, the clog cleared and intake resumed. So across its entire descent, the LMS collected 46 spectra across approximately 64 to 0.2 kilometers. This is an electron ionization mass spectrometer. So spectra collected 3 different energy levels across 128 units, but only measurements were taken at 232 mass positions, and that retained a good mass resolution, about 0.001. So what we showed over a course of several publications after release of this data to the public, which occurred in 2021, we showed that this LMS, this data set contains several uncharacterized trends in context of both mass and altitude. So in order to extract these trends, we went way back into the data and started to really analyze the internal standards and how the data was structured per se. So we started with analyzing the peak shapes for several internal standards of the data, and that included methyl from methane, argon 40, and argon 136. We then tracked the behaviors of all these internal standards at all altitudes, and that was looking at changes in mass errors and full width half maximum or peak shape. And then from this information, we were able to develop a peak fitting routine for target species such as water, oxygen, nitrogen, H2S, and others. So the long and short here, what this told us is that the mass analyzer, or the LMS, behaved nominally throughout the entirety of the descent, and that the data had good resolution and accuracy, which is important for us to know because we want to know how good this data set really was. So from here, I'm going to jump to some mixing ratios that we recently extracted. These are mixing ratios on the screen right here for SO2. Let me get this laser pointer thing out here. So these are mixing ratios for SO2 as measured by lots of previous measurements, including radio occultation, near infrared, gas chromatography, and UV spectroscopy. These are all the blue points. And then here are the mixing ratios we get from the LMS. They do not match the blue points at all. And in fact, they are incredibly high at 1000 ppm or more. So this is actually a very, very interesting result. And then we did the same thing. And I'm sorry, let me back up. And then here are the values from the Large Probe Gas Chromatograph, the LGC, which was on the same spacecraft as the LMS. As you see here, when considering their larger reported errors of 3 sigma, our values, LMS values, are within error to the LGC, but the LGC are also within error to the blue points. So there's a lot of uncertainty here. Or is there? So then we did the same thing for water, and we get actually a very similar trend for water that has the same shape as the SO2 profile. Now, what's interesting here, these are the measurements of the LGC, which were published many decades ago. Our values are right on the money over here. However, as most people probably are kind of barking inside their head right now, water, at least in terms of water vapor, has been measured at Venus several different ways, including near IR and optical spectroscopy, including GC, but this was sampling below the cloud layer. And all of these measurements point to about 32 plus or minus 11 ppm water vapor. However, if one actually just looks at other measurements that were obtained by sampling within the clouds, this would be the moisture meter on Vega 2, the GCM of Venera 13 and 14, and the hygrometer on Venera 13 and 14. All of these measurements provided high water if they sampled in the clouds. So then how is this explained in the literature? Most people just kind of disregard these measurements from the moisture meter, GC sometimes, and the hygrometer. However, what about the LMS measurements? In the original investigations in 1980, these trends over here mostly were attributed to the capture of sulfuric acid-based aerosols, pure aerosols made of purely sulfuric acid with a tiny bit of water. And how is that the case here? They attributed this bump in SO2 on the left and this bump in water on the right to the thermal decomposition of aerosols that would capture in the clouds and then begin to thermally decompose as the instrument dropped through the atmosphere. However, this bump for SO2 in the bottom or the lower atmosphere was left unexplained. And this bump, huge bump for water, was attributed to terrestrial contamination or water from Earth. We believe that that is incorrect. What we're saying is that these trends are the combined result of a capture of aerosols that have a heterogeneous composition or a mixed composition. What we are saying is that all of these measurements obtained from sampling directly in the clouds are actually accessing hydrate phase water in the aerosols, not vaporous water, not gaseous water, but water in the hydrate phase, most likely tightly bound. And then backing up, we remain consistent with the original investigation saying that sulfuric acid was captured, then thermally decomposed, but then we add and say that the bumps of SO2 and water in the deep lower atmosphere are the result of the decomposition of different iron sulfates and uncharacterized hydrates. So to give you kind of a cartoon version of what I'm talking about here, on the left would be an image of, like, let's say the LNMS inside the space probe, and this would be the border between the outside and the inside of the space probe. And this would be an idealized version of the inlet where gases are flowing into the mass spectrometer. So what we're saying based on our analysis of the data is that aerosols were inadvertently captured between 51 and 48 kilometers. That serves our aerosol collection window per se. And so the inlet then got clogged with certain types of aerosols. And this is evident in the data about a 6,000-fold decrease in CO2. Now, what is consistent with our analysis and the original investigations is that the aerosols then began to thermally decompose as the probe descended deeper in the atmosphere and the inlet started to heat up. Now, as a result of this, then intake then resumed approximately 25 kilometers. That's where the original investigations end. What we add is the following, and what we're saying is that certain aerosol remnants remained in the inlet, in the LNMS inlets, as indicated by these pink dots in the bottom. And then as the probe descended into the deep lower atmosphere and its temperature went way up, these aerosol remnants then began to further decompose to release gases in the LNMS. And that what we're saying is that there are several uncharacterized gases and compounds in the LNMS data set that relate to aerosol composition. So what we did is then focus on the kind of this part of the cartoon and how different species got released in the LMS based on the differential changes in temperature throughout the descent. Some of these gases and compounds include SO2, water, SO3, O2, as well as ferric oxide. So these plots on the bottom are better displayed in this plot or this slide over here. So how do we get all this information over here? So first of all, we found a way to extract number densities from the LMS data that was basically converting counts to number density, and we published these methods in MethodText in 2023. We also then were able to extract the LMS inlet temperatures, which were heated just above the atmospheric temperatures throughout most of the descent. We were able to extract this information using LMS project reports that we found in the NASA Ames archives, as well at UT Dallas. So then what we did is after I plotted all this stuff out with number density on the Y and inlet temperature on the X, I realized that these peaks, which did not look so symmetrical when they were altitude profiles, but all of a sudden when it displayed as a thermal release profile, these peaks were somewhat symmetrical. Hence, I then fit all these to Gauss functions, where the red line is the sum of the fitted peaks. Then from the Gauss functions, I got the peak areas, and the peak areas then relate to total number density. So what are some of the trends we see here? So consistent with the original investigations, the release of SO2 track between 50 and 25 kilometers indicated by the upper x-axis, or approximately 75 to about 280 degrees Celsius on the bottom x-axis. So these trends relate to the thermal decomposition of captured sulfuric acid, and it's consistent with the original investigations. What we're saying further is that both SO2 and water also, the release of SO2 and water also track in the deep lower atmosphere. And we're saying that this is consistent with the decomposition of metal sulfates, as well as hydrate decomposition. Further, in the upper right-hand corner, we show that SO2, SO3, and O2 track in the deep lower atmosphere, and that is consistent with sulfate decomposition. And then in the bottom right-hand corner, we also show that SO2 tracks with the release of ferric oxide. And just a note here, we are saying ferric oxide was released into the mass spec via our analysis of counts at 72 units, which we believe is FeO. So we believe that Fe2O3 is a thermal decomposition product of an iron sulfate that then got released into the mass spec, got ionized at 70 electron volts, and then fragmented to ultimately release FeO into the mass spec. So with this information then, what we're saying is that the aerosols between 51 and approximately 48 kilometers have a heterogeneous composition and includes sulfuric acid, iron sulfates, ferric sulfate specifically, uncharacterized hydrates, and a little itty bitty bit of solution phase water. And what we're saying is these aerosols got captured in the LMS and then thermally decomposed in a differential manner throughout the entirety of the descent. The thermal decomposition reactions that we are assuming take place are written here, and it's significant because we can see here that SO2 is released from both sulfuric acid and ferric sulfates. They'll be released at different temperatures, and we see that in the LMS. We also see the release of O2 at different temperatures. We also measure the release of ferric oxide via the counts for FeO+. And we also see evidence of at least 3 different forms of water. And that would be structural water, hydrate phase water, and solution phase water. So with this information in mind, all the abundances, our ability to get number densities, as well as the stoichiometry in these chemical reactions, we then basically subtracted structural water and got the following parameters and from the aerosol phase: weight percent, molality, bulk acidity, and mass loading. So these values are shown here in this table. And am I over time right now?
No, you're fine.
Okay, thank you very much. So in this table, there are 3 sections. There's aerosol constituents, aerosol water, and volatile fraction. So I'm going to take your attention to this first box over here, aerosol constituents. And what we're saying is that the aerosols are composed of 21% sulfuric acid, 15% ferric sulfates, and then 64% water. We're not saying this is all solution-based water. We're saying this is mostly in the hydrate phase. Before I move into water, I do want to point out that we also were able to get mass loading values, and our mass loading value for sulfuric acid is consistent with measurements from Vega 1 and 2 obtained by reaction gas chromatography. Moreover, our iron loading values in terms of mass loading are also consistent with measures from Vega 1 we obtained via X-ray fluorescence, and that our overall total mass loading is also consistent with measurements from the particle size spectrometer, which was also on board the PVLP, same as the LMS. So then in terms of aerosol phase water, what we're saying is that 64% is dominated by different hydrates. So we have 2 different hydrates. 61% of that 64% per se are hydrates with a temperature of dehydration or decomposition, either way you look at it, between 340 and 460 degrees Celsius, consistent with metal sulfates and other perhaps organic species, perhaps. And also 3% of water comes from hydrates with a temperature of decomposition between 50 and 250, such as sulfuric acid and or phosphoric acids, though we don't have any good evidence for that just yet. And then in terms of solution phase water, we're saying that only 0.2% of the 64% is actually solution-based water. Now, since we have built a thermal profile, if you will, we're also able to estimate what is in the volatile fraction of the aerosols, or what would actually vaporize out in the volatile section, if you will. And what we get is approximately 87 or 90% sulfuric acid. And I want to point out that that value is completely consistent with measurements obtained by polarimetric and near-infrared spectroscopy, with, say, 75% sulfuric acid. So then in conclusion, I want to say that our data points to the following statement, that the aerosols in the middle and lower clouds have a heterogeneous composition that contains sulfuric acid and iron sulfates in roughly comparable masses. And we also have evidence for an unexpected reservoir of water from hydrated compounds. These hydrated compounds include hydrated iron, magnesium, other metal sulfates, and some other uncharacterized species. I also want to note that most of the abundances we get right now are also consistent with all prior Venus measurements, which means we're not completely out to lunch. And that our measurements give or suggest a bulk acidity value that's constrained at a pH of -5 or less. And we also want to state that we believe our work illuminates the potential cosmic origin of iron. So where does this iron come from? It could either come from vapor phase, from the vapors from the surface, or it can come from cometary space-time input into the clouds. So our collaborator, Misha Zolotov, is definitely pushing the cosmic origin part of that theory. So then I think holistically what this work shows is that Venus's clouds, especially in the middle and lower cloud region, remains really understudied. I want to indicate that further analyses with this data set are underway. And with that, I'm happy to take any questions. I also want to thank funding. So I have some NASA funding to support all this as well.
Okay, thanks, Rakesh. Yes, ma'am.
Very interesting. I'm wondering, do these really hydrated aerosols have significant implications for interpreting the D to H measurements of the vapor, of water vapor?
Yeah, that's a darn good question. I'm going to stop sharing so I get to this. Yeah, I think so. I would think so. We have soft evidence right now that the water that's in the hydrate phase is actually enriched in hydrogen. So that could have an impact on a global calculation level for the water budget. We're not sure yet, but that's where we're headed. And I do think it does have an impact on the D-to-H ratio.
Plus, the DDH ratio is all over the place in this atmosphere. You know, these more recent observations, it's like, what, 200 plus in the top of the atmosphere?
Way up, right?
He didn't show the profiles, but we see it going all over the place. And I think another thing that Rakesh showed here, which he went through kind of quickly, but I think it's amazing that all this stuff matches previous spacecraft data, a lot of which, as he said, was dismissed. People thought these Vega and Venera values were just garbage. But now we're showing a lot of the stuff is completely consistent with that because we understand the data better. We understand the processes better, right? Also, this whole issue with, you know, there was this huge amount of water that they detected in the bottom of the atmosphere, and Chris didn't have time to explain it, but they were saying it was terrestrial water, meaning the spacecraft suddenly outgassed like, you know, half a liter of water from the interior, which is completely ridiculous. The spacecraft couldn't have possibly had that much water in it. And we're saying, no, I mean, it's in all these different phases. So I think, anyway, this is amazing work. And this guy has done most of the heavy lifting. And the rest of us are basically just cheerleaders.
Thank you for the nice word, Mike.
Rory.
Yeah, I agree. It's great stuff. I guess I want to make sure I understand a part of this. You know, a lot of the water that you're saying comes from these hydrated species. Does that mean, but then you said there was a soluble part too, and I assume that just means sort of free water, like actual just H2O molecules floating in the atmosphere?
Yeah, imagine like a bag of molten sulfuric acid in the liquid phase with a little bit of water. So they're forming the liquid phase. And then inside there, it's a question mark of what phase are these iron compounds and hydrate species? Like, we don't know. Depending on the vapor pressure, they could be all in the soluble phase, or they could be suspended crystals or suspended precipitates, like amorphous materials.
Yeah, and so then the original water altitude profile you showed, was that then like the sum of all of those sources? Or
Yep, that's the sum, right.
So then is there a way to, I mean, maybe this is not possible, but then remove the hydrated material and actually get it like the actual water vapor profile in the atmosphere? Just
that's in the air bars. It's so little, it's in the air bars.
It's in the air bars, okay.
Yeah.
Yeah, I guess I'm trying to get at just what is sort of the bulk abundance of water in the atmosphere that is not bound up in other minerals.
It's small.
Yeah, but it's measurable.
But it's very small.
It's a very interesting tracer of geodynamic processes, right? So to get at that would be really valuable. Right. So I guess I don't know if it's not measurable with this data set, fine. But
right. But also what Rakesh was pointing out was that we think the origins of some materials in this atmosphere are cosmic. Like, yeah. I mean, he said cometary, but also just chondritic materials falling in. We sit on Earth, and that could be.
My bad. Yeah, I meant chondritic. That's my bad.
Yeah. So that's just coming in. There's going to be water in that stuff. That's gonna play some role, especially at these small, very small abundances, and this stuff is just coming in all the time, as we know.
Right.
That makes it much more complicated.
Yes. I
But
didn't
thank God we have Zolotov on here, because he's the one that like pointed this out to us. Hey, dummies, this is where the metals are coming from, probably, you know?
Yeah, it was weird to see Fe2O3.
Because we were thinking, oh, it probably came from the surface. It's like, no, it came from the top, man.
Yeah. I hadn't thought about that. So the water could be exogenous.
Could be.
Yeah.
Could be some of this
It
water.
could
some of-
be, yeah. And we have some other crazy evidence. We're not really ready to publish it yet, but we did partially publish it. Our S34 and S33 ratios to S32 are actually pretty high. They're within air, I think, to the Earth values, but they're on the high level. So I think space dust per se often has a higher ratio for sulfur isotopes. So yet another example where maybe things in the clouds are coming from above and not from the bottom.
Yeah, it's something Sonny just pointed out, that the chondritic water will have different isotopes, obviously, abundances, so.
Can you remind me, is Da Vinci still, has it been postponed, or is
No,
it
Da
still on the
Vinci's
map?
going forward. It was Veritas that was postponed.
Just Veritas.
But yeah,
But
so
is there like a
there is a
probe?
high-res mass spec. It's a quadrupole mass spec, the same one that's flown on Curiosity.
Yeah.
And as Rakesh would say too, we thought for years they were not gonna open up the inlets in the clouds because they were terrified they would get clogged, the same as this. But we recently reviewed a paper of theirs, and between revisions, they changed the diagrams. And now they're saying they are gonna open one of the inlets in the clouds, which is really important, because if they can keep it open, maybe we'll find out if there's pH3 in the clouds or if it's H2S or whatever it is. Because in this instrument, those are isobaric. They're the same masses, so we can't.
I want to say what's really going to complicate everything is that we have a paper under review that there's a couple lines in there. We'll probably stress this later. Is that every instrument that sampled in the clouds sampled aerosols. I think if you look at all of the data, everything that sampled water in the clouds has a high value. There's even a UV spectrometer. I think I showed this profile. I can show it again. You can interpret it also as evidence of a clog, like a partial clog in their instrument, but they didn't interpret that way. If you don't, can I show it to you guys? You want to see it?
You got a couple.
All right, let me get to that.
The target year for the launch would be what, 2030s?
Launch is around 2030.
Yeah.
For all these 2030,
Oh,
2032.
whoops. I got out of here.
Yeah, he died there. I mean, I think last time I visited Da Vinci, they were talking about the need to make the probe slightly bigger because they couldn't fit everything in. And that set off.
You guys see this dotted line here, how it dips? It comes back up, it comes down. So this dip was interpreted as two different regions of SO2 concentrations, like two specific bands, not a well-mixed atmosphere at all. That's the old school paper. I think it's a Surkov paper that said that. I may be wrong in the author actually. So that's the old school interpretation, but that little dip corresponds to right where these aerosols that got captured begin to degrade. And then I was saying before that we have a collection window of about 51 to about 48. That matches with that. So what we're saying is that this instrument here probably also experienced a partial clog, but the way it was engineered was different. It had an inlet tube that pointed down, and it had an outlet tube that pointed up. So during the descent, particles went in, and then some particles went out. And I think it partially clogged, but also their inlet tube was like 10 times bigger than the LMS inlet. So it allowed things in, but it also allowed things out. And then soon as this instrument cleared the cloud deck, it cleared out. But then what's also interesting, I don't know if it's all dirty now. Let me see if I can get rid of all this junk I put here. So you guys see that this is also somewhat unexplained, is why this value goes down instead of just being basically straight down. That's yet to be explained. So what we think is that whatever got clogged over here started to cake on the edges of the mirrors and started to occlude whatever light could be passed through. That's like one theory we have right now. And the reason I'm saying that is because as Da Vinci's going to sample all the way throughout the clouds, I think there's actually a good history that everything that did sample in the clouds sample the aerosols. So that could be a good thing, but I don't think Da Vinci's ready for that yet. If they just want to do gases.
Yeah, which they do, right. And there was this idea, they also have this laser tunable spectrometer. So they've got like, what was it, 4 species that they're going to measure? And that was going to measure in several places, including in the clouds, that you don't have to worry about clogs. And there was a competition or a contest? Like they wanted to pick another channel. And one of the possibilities was PH3, of course, everybody's interested in. But in the end, after everybody submitted it, and we submitted, I think we submitted ammonia, right? Isn't that what we wanted?
Yeah, ammonia, yeah.
They decided they would not add another channel because it was too expensive. It's like, okay, great. So, but anyway, yes. Okay, thanks.
Can I ask a
Oh, yeah.
chemistry
Yeah.
question
Oh yeah,
real
sure. Go
quick?
ahead. Ask a chemistry to chemistry.
So yeah, I really enjoyed seeing some chemistry here.
Yeah.
So I was wondering, you mentioned that there was structural water in sulfuric acid, which was part essentially of the two acidic hydrogens, right? But sulfuric acid is also hydrated with water, which you also counted as structural water in the iron oxides, right? So typically sulfuric acid comes with 3 waters, or maybe 1 water, depending
I'm calling that hydrate phase water. If it's hydrogen bonded, I'm calling that hydrate phase water.
Okay, so I don't remember seeing that in your slides. Have you accounted for that?
Yeah, I have. I might not account it specifically in the slides with the calculations. Yeah. So what we see is that what the release of sulfuric acid and water happens similar. It's similar temperatures, and it's a ratio of maybe 1 sulfuric acid to less than 1 water. So there's really not a lot of water around.
Hydrate water.
Right.
Okay, so you have less than 1 hydrate water per sulfuric acid, and then you have exactly 1 water structural for sulfuric acid.
Correct.
Right? Okay, thanks. Okay.
Yeah. Okay. Any more chemistry questions? Good. I'm glad we have our chemists here to ask chemistry questions.
It's important.
It is, absolutely. Okay. Well, thank you so much, Rakesh. That was great. And thank everybody today, especially everybody who stuck around. So, see you all tomorrow. And thank you, Arnaud, again, and Rakesh. And
thank you.
Have a nice evening out there on the West Coast.
All right. Thank you. Bye.
Out.